All right. So what you're about to witness is the culmination of 10 weeks of intensive research by 8 very talented undergrads that we gathered from all around the country. So you're going to see a myriad of topics from lab-based atomic physics all the way to solar flares. So you're going to get the whole gamut of the solar physics curriculum, more or less. We're even going to have a talk about, Europa. It's going to be pretty cool. So, all right. We're going to start off with 2 talks. We'll have 2 coffee breaks in between every 2 talks. We'll also have a lunch break. Lunch will be provided. Hopefully it will be here in time. So, feel free to have any refreshments in the back. So there is fruit. There are various pastries and Nantucket nectars, so have fun there. So we got a couple minutes here, so we're going to kind of sit tight, and then we'll get ready for Gianna to be the first sacrificial lamb here. So, and she'll be talking to us about the EBIT system, which is an atomic physics experiment that we have at our CDP campus. So we'll get started in just a couple of minutes. All right, so let's get started with our first talk. So we have Gianna Longo. She's from the University of Hawaii at Mānoa. So she's going to talk about the EBIT system, which is a cool little atomic physics experiment we have over at CDP. So take it away.
All right, thank you, Chad. So like he said, my name's Gianna Longo, and I'm visiting here from University of Hawaii. So this summer, I designed a compound injection system for the EBIT for solar physics applications under my mentors, Amy Gall and Adam Foster. Let's see which way this goes. Oh, maybe? Okay, so during this talk, I'll walk you through the science motivation behind my research. I'll walk you through the EBIT, what it is and how it works. I'll walk you through my design and what I worked on this summer, and then also what we're looking at for future plans. So let's go through the solar physics applications and the missing data that we have in our databases. So the biggest question that solar physicists ask is, why is the solar corona so much hotter than the chromosphere beneath it? And to study this, scientists can look at different phenomena like solar flares or CMEs, but we can also take spectroscopic data of what makes up the corona. However, when we take this data, it's often filled with lots of different temperatures, densities, or different ionic species within the spectrum. So if you take a look at this top spectrum, you can see that there's various temperatures and densities. This is because there are fluctuations inside the corona. This is just a modeled spectrum of the sun from the Chianti database. So on the bottom, we have a series of iron ions, all indicated by different colors. You can see right there. So all of these lines kind of blend together. All of the different colored lines will blend and overlap, and it's very hard to get accurate measurements from these lines. And when you're doing really complex calculations in a lab, you want to get as accurate as possible. So here's another example of just some ambiguous features on a spectra. The blue is an observed spectra from 1972, and the black is a modeled spectra from the Chianti database. This is the bandpath that Muse is looking at, but in the EBIT lab, we're focused on everything from 90 to like 200 angstroms. So we have some question marks here, and you can also see that the model doesn't perfectly fit the data. And this is because when we don't have accurate measurements and you're doing these complex calculations, it's very hard to get an accurate fit for your lines. So in the lab, we can use what's called an EBIT. This is an electron beam ion trap, and we can use this to kind of mimic the density of the solar corona, and we can create any ion that we want inside the lab, and we can add this to the atomic databases. So what is the EBIT and how does it work? Here's a good video from the NIST website. We shoot a beam of electrons at a neutral gas to trap and create highly charged ions. When the electron beam hits this neutral atom, it's going to have electron impact ionization. This means that the electrons will interact with the atom. They'll strip some or all of the electrons off of the atom, creating a positively charged ion. This removes the electrons. It's kind of slow, sorry. The positively charged atom will then be attracted to the negatively charged electron beam, and this is how we trap the atoms within the drift tubes. So once they're trapped in it, we can have further collisions that will excite the electrons to a higher energy level, and when they naturally bounce back down, they can release radiation in the form of a photon, which we pick up on our CCD detector, and we can get experimental spectra from these. So let's take another look at that solar spectrum. I want you to remember how saturated this spectrum is and how many lines overlap and how many different ions you can see. Everything from iron 7 to iron 22, and this is just between 90 to like 160 angstroms. So now we have the EBIT spectrum. When we use the EBIT, we can tune the electron beam energy to create any ion that we want. So we're able to get super isolated lines that don't overlap with the other ions that you would normally see in the solar corona. So already, if I'm going to do a calculation with this data, it looks much better to use lines like this that are way more accurate than have everything blended together like you can see over here. So this is what I worked on this summer. We were motivated by the need to study these iron ions within the solar corona, but the EBIT uses gas for its injection system. So I was posed with the question, how do you vaporize metal iron to inject it into a vacuum chamber? So here on the left is the existing injection system on the EBIT. This on the right is how I would tweak it to add my injection system that I designed. So let's walk through how this works. On the top, you can see what's called a precision valve. This can be adjusted from this knob, and you can adjust the count rate of the atoms going into the injection system. They will enter through a 5-way cross on the top, and this one operates at a pressure of about 10 to the negative 6 torr. So we're going from a high pressure entering the precision valve to a very low pressure inside of this 5-way cross. The atoms through this, some will disperse and they'll be pumped out of the system. Some will go through an aperture that's about 0.04 inches into a bottom 4-way cross that operates at a pressure of about 10 to the negative 8 torr. So our pressure is dropping as we go closer to the EBIT, which guides the atoms through the system. Those atoms will also be dispersed slightly, but some of them will form a ballistic jet and go through two 0.015-inch apertures into the EBIT, which operates at a pressure of about 10 to the negative 10, so a near vacuum, and also has a temperature of 4 Kelvin. So it's super cold and very low pressure, and this is where our electron impacts occur. So how are we going to vaporize the iron? I decided to use a MEVOX system, and MEVOX stands for metal ions from volatile compounds. And a volatile compound is simply an organic compound that has a high enough vapor pressure to evaporate at room temperature. So we don't have to heat anything up in order to use this system. And you'll see in the next slide, our compound is super dangerous to use, so we wanted to avoid heating it up at all costs. The MEVOX system also allows us to adjust the count rate, like we saw with this precision valve. So we can also adjust the charge state balance, which is the balance between ionization and recombination. So it gives us a lot of control of what we're putting into the EBIT. So these were the two compounds that I researched this summer. The ferrocene we already had in the lab. This is what we thought we were going to use, and we realized later that we would have to heat it up. So ferrocene and iron pentacarbonyl both have iron as their heaviest element within the compound, so it takes the most energy to ionize it, and that would show up in our EBIT spectrum. The ferrocene has a vapor pressure of 0.009 torr, so if we were to evaporate it, it comes as a solid and we would have to heat it up somehow. The iron pentacarbonyl, in contrast, is a volatile compound. It has a vapor pressure of about 21 torr, so it comes as a liquid and it'll evaporate at room temperature, meaning we don't have to do anything to it. It makes it a lot safer because you can see here in the cons that both of them are extremely flammable. Iron pentacarbonyl has a flash point of like 5 degrees Fahrenheit. So we want to be super careful when handling this in the lab because if it were to catch on fire or if we were to breathe it in, it could be deadly. Additionally, I used the ideal gas law to calculate the amount of molecules that would be in a 1 milliliter sample of both of these, and you get a lot more iron pentacarbonyl. So overall, this definitely seemed like the right choice. So when handling the iron pentacarbonyl, we have to be super careful. So during the transfer of when we get it in a container to putting it in the container that is connected to the EBIT, I had to come up with an entire safety procedure. So a quick overview of this is we're going to use a glove box, not like the one in your car, but the one like this that has gloves inside a controlled environment. So iron pentacarbonyl reacts with oxygen, but it can exist in a nitrogen atmosphere, so we can connect a gas line right here after putting all of our materials in and flush the system out with nitrogen. This will also be under a chemical hood, so anything that would leak out will be flushed away and not in contact with us at all. Once everything's inside, we're going to use a syringe to syringe out 1 milliliter of the liquid and put it into our container, which will be closed with a valve that we can turn on and off. Once it's put into that cylinder that we're going to attach to the EBIT, we can remove everything and exhaust it through the hood, and it'll be ready to be moved to the EBIT lab. So this was my first design. I didn't know how to use CAD when I started this, so this is a very rough 2D sketch. So my first thought was, why don't we just put it in a glass cylinder and hang it off the side of the EBIT? And what do you think you get when you put a deadly flammable liquid inside of a glass cylinder 6 feet in the air? You get the risk of it falling and shattering and everything exploding. Not actually, but fire. So we decided we needed something else, something a little safer, and I thought we should put it in a box. We should tuck it away from anywhere where it could leak and attach it to the wall. So you can see here, this is called a lecture bottle cabinet. Simply put, you can put things inside of it, and it will exhaust out of the building, as you can see from this red line, and will also be connected to exhaust on the EBIT. This is a lot safer because you can control everything that happens inside the bottle cabinet, and if it were to leak, it's confined to its enclosure. So these green lines show where the iron pentacarbonyl will travel through the system. We have a control valve, which means the iron pentacarbonyl can leave it, but it can't go back the way it came from. We also have on-off valves, which give us control of when it's flowing and when it's stationary. So here's another look at the lecture bottle cabinet. You can see that the exhaust is up here, and we can open it right here. So this is a look at my 3D design because I became a master at Onshape. And this is what it would look like inside the lecture bottle cabinet. So we're going to have to drill some holes here on the left and here on the right. Again, the iron pentacarbonyl has to be flushed with nitrogen if we were going to remove anything. So this is where the nitrogen line will be connected to, and this is where the iron pentacarbonyl will leave the system into the EBIT. So taking a look at this 3D design a lot closer, this is the step-by-step process of how the iron pentacarbonyl will be injected into the EBIT injection system. So we can start by opening this valve here. We can let a little bit of nitrogen into the system just to neutralize everything. Once that goes through, this sample cylinder is holding our 1 milliliter of iron pentacarbonyl. This on-off valve can be opened, as well as this valve 5 right here, and this will start the flow of the iron pentacarbonyl gas. So that will travel up and past here. We also have control valves that will let it go one way, but not back the way it came from, and it will travel through this elbow and up into the EBIT. It will also be monitored by this pressure gauge, and in the unlikely event where this were to exceed 30 psi, I've included an auto overpressurization release valve, which will monitor this and release any extra gas up into the exhaust. We've also checked with the safety directors in the lab, and the exhaust does exit the building, so the iron pentacarbonyl is not going into anyone's office. So let's take a look at what's next for this project. I came up with an order form. As you can see, things are a little pricey once you get down to like the lecture bottle cabinet and the additional pumps, but give or take, we're looking at a budget of about $15,000. So once we run the final design by the engineers and the safety directors, we can go forward with ordering these parts, and hopefully by about January or February, we'll have this built and ready to take measurements. I'd like to thank my mentors, Amy Gall and Adam Foster, as well as Kathy and Chad for running the REU, the CFA for hosting all of us and for all the free food, and also the Smithsonian Astrophysical Observatory for letting me use their lab.
Hey, that was fantastic, Gianna. All right, so we have plenty of time for questions, so have at it. Kathy.
So, microphone. So you talked about how you get the your iron compound into the EBIT. Then what happens? Do you have this
then it passes
stuff
through
in
that system. Yeah.
in the EBIT? Like, is there any concern about the stuff, the iron compound staying in the EBIT or being dangerous there?
So once you're ready to flush it out, that's why we have the nitrogen line, because you can pump the nitrogen through. There's also pumps, I think in this slide. There's pumps on the EBIT that will exhaust it out of the EBIT. So once it's flushed with the nitrogen, let's see, I think it's in this slide. We have exhausts that leave the EBIT, so we can pump it out, and we're using an oil-based pump so we can clean it out afterwards.
All right, also for those watching online, so please type your questions in the chat. There is about a delay of like 2 minutes or so we'll probably get to them towards the end, but I'll be looking.
Mm-hmm.
Srijan.
Hi, very nice presentation. I had two questions. First, I remember you were talking about ferrocene a lot in the mid-presentation. Why did you again decide to switch to iron pentacarbonyl? And second is, what happens to the iron pentacarbonyl after it's released outside your system? Is it just exposed to the atmosphere, and is it harmful for us?
So for your first question, we were using ferrocene up until the mid-presentations. I think literally the day after we started looking at iron pentacarbonyl. We started with ferrocene because we already had it in the lab, and we were thinking about using other systems where you would heat it up. Then we decided on the MEVOX system, and we realized that we could find another compound that didn't need to be heated. So the basic answer is we already had it. For your second question, we're only using 1 milliliter of iron pentacarbonyl. So whatever does get exhausted out of the EBIT, because a lot of it will go into the EBIT and get ionized, whatever does get exhausted will be such a small amount that it won't affect anything.
Allie.
So you mentioned that you're using the iron pentacarbonyl and you can see the iron spectral lines and the nitrogen spectral lines. Since nitrogen pentacarbonyl also has carbon and oxygen, why can't you see those spectral lines?
So since iron is the heaviest element in this, it takes the most energy to ionize. So since we're looking at only like 90 to 200 angstroms, the oxygen and the carbon might get ionized as well. However, it would take so little energy because they're so much lighter that you wouldn't see them on our spectrum.
Roberto.
So you mentioned that you're using nitrogen to flush your system. Is there a reason why you're using that specific element?
We have it. So it can exist in oxygen, and it's easy to get a nitrogen tank into the lab, so that's why we're using that. And all the safety data sheets that I read up on, they all mention nitrogen.
All right, we do have a question from the chat. So it says, amazing talk. I was wondering if there is a hope of continuing similar work to look at different metals, or are you focusing only on iron?
I'm focusing only on iron. I haven't researched other metals, but I suppose if you wanted to use another volatile compound, this MEVOX system could work as well, as long as you flush the iron pentacarbonyl out.
John.
If I remember correctly, people were using iron carbonyl in a lab downstairs in the basement here with a spectrograph in the 1970s, and I'm sure it wasn't nearly as safe.
I bet it wasn't, considering we were going to use this.
Sam.
You mentioned the EBIT can basically reproduce what the corona is like. You said coronal densities. I was wondering roughly what kind of densities we're talking about, or maybe what altitude in the corona that kind of gets to.
What density we're talking about?
Yeah.
It's about 10 to the 11 electrons per centimeter cubed.
So really low down, close to the surface.
Yeah.
All right, Penny.
This is a bit of follow-up. How much can that be altered? Is it one density that you can replicate, or can you adjust that?
I believe it's one density. We have control of the energy of the electron beam.
Any other questions? All right. Amy.
A bit of a personal question. I was just wondering what your favorite part of this project was.
My favorite part was this learning about the safety, because I feel like it made it sound really cool. Like talking about how deadly these compounds were, where it's kind of just a flex when I tell people who don't know much about this. So that was my favorite part. And learning to use Onshape, because it's cool to learn 3D after doing all 2D designs.
All right, if there are no questions, I have Laura has a question.
I'm curious as to, you said that the iron pentacarbonyl comes as a liquid, but you have to evaporate it. Like, how does it go from being liquid? But it also says that it can evaporate in room temperature. How does it go from being a liquid to like being evaporated and ready to use?
So because it has such a high vapor pressure, when it enters room temperature, it will start to evaporate. So we contain it within the cylinder, and there's like an equilibrium between the gas and the liquid. And once we start pumping it out, that gas will be attracted to the lower pressure system, which will pull it from the sample cylinder.
Any other questions? So I have one, and that is, so you have all these iron ions that are going to be in this system. So we have an idea of how many molecules per second will be passing through, but how many photons do you expect to actually get out of this?
Oh, I think that depends on how long you take measurements for.
Yeah. Oh, yeah. So anywhere from, could be from a second to a month, or
run it for a few minutes at a time to a few hours.
Okay.
But you get enough to read the spectrum. I don't know the exact number.
Yeah. I do have another question. So you're dealing with these insanely toxic compounds. I mean, you look at ferrocene, that thing is absolutely cursed. It's just like cancer in a dumbbell.
Yeah.
So there are definitely other solar ions, such as like argon, which of course is completely inert, which still has some spectroscopic use for solar physics. So is there any idea of maybe using that?
We already have that on the EBIT.
Ah,
So we have a few gases. We have argon and neon, and I think helium or xenon. So those are already being tested. We already have data from those. So
Excellent.
we wanted to go the next step.
perfect. Penny.
How do you move the iron pentacarbonyl from the glove box to the other box?
Very carefully. You would wear full PPE, which is personal protective equipment. So we're talking gloves, possibly silver gloves. Our safety director is still looking into that. Lab coat. All the safety sheets said not to wear a respirator unless it catches on fire. So I would still wear a mask, hairnet, goggles, face shield, and clear everyone from the hallways. And it's completely sealed, so you do have control of that. And it's filled, the sample cylinder is filled with nitrogen, and it's such a small amount that most likely nothing's going to happen. But you would have to be pretty mindful of where you're walking.
Yeah, lab work is a blast. All right. Any other questions? We have probably time for one more. All right. If not, let's thank Gianna again. All right. So.
Hello? Oh, here we go.
All right. Up next, we have a talk that's kind of solar adjacent. It deals with plasmas. Plasmas are plasma everywhere. So this is actually going to be talking about Europa and a planned NASA mission called the Europa Clipper. So this is Allie Dunkhase. So she's from San Diego State. So, Anne, whenever she's ready, she'll take it away.
Hello, everybody. My name is Alexandria Dunkhase. I'm from San Diego State University, and my research project this summer has been on Europa Clipper applications of neural networks for identifying ion compositions in Europa's plasma environment. And my mentors are doctors Michael Stephen, Srijan Das, and Yemi Rivera. Oh, it needs to be on. The outline for this presentation will be as follows. First, I'm going to be talking about the magnetic induction at Europa, which is one of Jupiter's icy Galilean moons. Then I'm going to be talking about modeling the PIMS response function. And finally, I'm going to discuss utilizing and training a neural network. So first, I'm going to be discussing about the magnetic induction at Europa. As I mentioned, Europa is an icy Galilean moon of Jupiter, and it is one of the biggest candidates for life beyond Earth within our own solar system. And because of this, NASA is launching the Europa Clipper mission, hopefully in October of this year, and hopefully reaching Europa by April of 2030. A big reason as to why it is a candidate for life beyond Earth is because of its subsurface saltwater ocean. Within this subsurface saltwater ocean is hypothesized hydrothermal vents, which are great for life beginning because they are a source of nutrients, organic compounds, and an energy source. This is actually very similar to what was seen on Earth billions of years ago when life first started forming. So a big reason as to why we're looking at Europa again is because of this subsurface saltwater ocean. But how do we know it is saltwater? So let's do a little experiment. Let's say we have Europa, which is in Jupiter's magnetosphere, which is in Jupiter's magnetic field lines. Jupiter has a rotation period of about 10 hours, which means that its magnetic field lines also rotate in a period of 10 hours. Let's say you were to take a conductor, such as saltwater, with a conductivity of about 10 Simon meters. You would predict that this conductor has a skin depth of about that of Europa's radius. And for those who don't know, the skin depth is the distance before a magnetic field effects start to dissipate. If this conductor was less conductive, like fresh water, the skin depth we would observe would be much greater than that of Europa's radius, so we know that can't be the case for its components of its subsurface ocean. Now, continuing to talk about saltwater, we know that it obeys Faraday's law of induction. This states that if you put a conductor through a magnetic field, this generates a current to flow, which then creates a changing electric field, or the curl of an electric field right here. The curl of an electric field causes a changing magnetic field, and this actually creates a secondary magnetic field. This changing secondary magnetic field reduces the primary magnetic field. Again, this is known as Faraday's law. If you've taken physics E&M, you might know this equation. This is actually what we observe with the magnetosphere around Jupiter. So, how do we know that these changes in the magnetosphere are actually due to Europa? Well, the changes in Jupiter's magnetosphere, the period of these changes correspond directly to that of Europa's orbit. It's about 3.5 days, which is the period of orbit of Europa. So all of this supports the theory that this subsurface saltwater ocean does indeed have effects on Jupiter's magnetosphere. So again, the whole basis for this is the changes in Jupiter's magnetosphere and the effects that Europa has on this. But there are other things in Jupiter's magnetosphere that causes changes in the magnetosphere, and one of those is plasma. If you don't know, plasma is essentially just hot ionized gas. And this plasma originates from either the volcanoes on Io. Io is another one of Jupiter's Galilean moons, or from geysers on Europa itself. The plasma around Europa typically consists of atomic and molecular oxygen, atomic molecular sulfur, hydrogen, and electrons. So we know that the plasma alters Jupiter's magnetosphere, and we want to see these effects. Well, these distortions actually depend on the total kinetic energy of the plasma. And in order to know the total kinetic energy of the plasma, we need to measure the plasma's temperature, its ion speed, and its ion mass density. So the underlying goal of this is we want to measure these plasma effects on Jupiter's magnetic field in order to know actual properties and understand Europa's subsurface ocean and the effects it has on Jupiter's magnetic field. So how can we do this? This brings me to my next point, which is modeling the PIMS response function. So what is PIMS? PIMS is the Plasma Instrument for Magnetic Sounding, an instrument that is aboard Europa Clipper. Its whole goal is to measure the magnetospheric plasma around Jupiter and the Europa ionospheric plasma. To do this, it is equipped with 4 Faraday cups. But what is a Faraday cup? A Faraday cup is an instrument used to measure the current produced on these segmented collector plates right here. Ions and plasma coming in must have a certain energy per charge in order to pass through the Faraday cup. If you're able to equate the electric energy to the kinetic energy of the incoming ions, you can actually rewrite this equation for the voltage. And for each ion, since they have a set mass and a set charge, we can see that the voltage is proportional to the velocity by velocity squared. This means that if you set your voltage to a specific range, this only allows for ions of a certain velocity to enter in the Faraday cup. ions that do not have this range of velocity or this range of energy per charge will get repelled by the Faraday cup and will not be allowed through. This is important because we're trying to measure specific plasma in Jupiter's magnetosphere that has a velocity of around 90 to 100 kilometers per second. So any plasma not within that range will be repelled out. The Faraday cups are using these segmented collector plates that are split into these 3 tridents. This is the part of the Faraday cup that actually goes through and measures the current. And the whole reason for the Faraday cups having these plates being split into 3 parts is because the amount of current collected on one of these tridents, the name of the segments, will tell us about the angle of the incoming ions and tells us more about the geometry of the plasma flow. So we can use this to make more accurate measurements and get more accurate data. So going back to the Faraday cups, this is the layout of the Faraday cups on the PIMS instrument. As you can see, they're oriented, each one 90 degrees from each other in a shape of a cross. Each one is in 3D space, so we can have a coordinate system for each one. But that kind of became one of the biggest issues with doing this research is how do we go from having one central coordinate system and axes for an entire spacecraft to 4 individual ones for each individual Faraday cup? To answer this question, I made an assumption saying that let's call cup 1 our central axes for the spacecraft. If we call cup 1 the central axes, then we can see that the spacecraft rotates about its x-axis. So it's only changing in the y and z direction. With this, if we want to translate this into a axes and coordinate system for each individual Faraday cup, we would need a rotation matrix that is constant in the x-axis. So this is the rotation matrix that you would use. This is stating that ions would be coming in at an angle alpha and with a speed or velocity of v. So if you operate this incoming velocity with this rotation matrix, what you get is velocity components for each individual Faraday cup. So you're able to get velocity in the x, the y, and the z direction for each individual Faraday cup. With this, you can plug these velocity components into this equation and get this theta value for each Faraday cup. And this is important because you can use this in the instrument response function, which is essentially the instrument sensitivity when it comes to measuring the current of these ions. So you can actually use this response function in this equation for measuring the total flux of the current, where the omega is the total charge flux. This is the phase space perpendicular to the discriminator. This is the phase space selected by the discriminator. This has to do with the instrument field of view. This is the mentioned response function of the instrument. This is the velocity going into the sensor. And this is the phase space density of the plasma. In order to get the phase space density of the plasma, which is essentially how much ions are in this portion of phase space, we can use VDFs, or velocity distribution functions. What is a velocity distribution function? In my case, it's essentially just a Gaussian distribution of the current over the voltage. And I know it might be confusing. Why is it voltage instead of velocity? But remember, you can use voltage and velocity interchangeably because they're proportional to each other. So in this Gaussian distribution, I graphed it for the current over the modulated voltage. And this is what is going to be measured by Europa Clipper. We will be getting these VDFs. But the issue is that when we actually get these VDFs from Europa Clipper, we're not going to be getting these spectral curves for each individual ion species. What we're going to get is a curve for the entire total summed ion species. This is not ideal because we want to know properties about each individual ion species, and these lines tell us a lot about different parameters that go into creating these VDFs. So if we add in the response function, we can actually get a more accurate view of what these VDFs look like. We can create these for each individual Faraday cup, and the amount of current within each individual Faraday cup, again, tells us more about the geometry and the angle of the incoming plasma flow. Additionally, if you take the area or the integral under each one of these curves for a specific range of voltages, you get the density of the plasma. So you get how much plasma and how many ions are in with each curve. So again, it's very important that we know we have these VDFs and we get this information about the plasma. But unfortunately, when plasma is really hot, which it is, the data becomes very ambiguous. The curves kind of overlap on each other, and we don't get these very nicely distributed Gaussian peaks. So we have to look at different parameters that go into creating these Gaussian distributions. Some of these include the co-rotation speed, the isothermal temperature, the proton abundance, the electron density, the oxygen-sulfur ratio, different oxygen and sulfur atomic and molecular ratios, and the angle of incidence of the ions coming into the Faraday cups. So my next step with this was to actually simulate some data for generating these VDFs. So I took a parameter range that is somewhat realistic to what you would actually see out by Jupiter, and I simulated data and got these VDFs, these current versus voltage VDFs. A big reason as to why I did this is I want to see how changing specific parameter values change the overall curve. So as you can see here, or if you can see, I have these different values for the oxygen-sulfur ratios, and you can see how changing the oxygen-sulfur ratios went through and changed the VDFs and the spectral lines. But again, we still have this main overlying problem. There's so much overlap between the VDF curves, and the data is way too ambiguous for us as humans to make definitive statements about it. So that is where we get to my final part, which is training a neural network. But why use a neural network at all? Neural networks are actually really good for curve fitting, and they're very effective and methodical, and they're actually very good for reading ambiguous problems and reading ambiguous input data. So a big reason why I use these is because they're really good at learning Gaussian distributions and Gaussian data, and they're really good at reading input parameters and getting expected output parameters, and they're good at simulating what the equation going into those would be. Additionally, they're conveniently powerful and very effective, off the shelf. They're quite simple and easy to use, and they're very easy to learn. And another thing that's really ideal about neural networks is that it follows its training. You can modify or change your model, and as long as you train it to fit your model, it will do the training. It won't go astray. It'll make sure to learn what you want it to learn. It's a very good training tool to have. So how exactly did I do this? What did I do with the neural network? So again, I used my simulated currents and parameter values to train the neural network to identify specific parameter values. So in this case, before what we had was a bunch of parameters going into creating a current value. But now I'm using the current values as an input and trying to train it to know the parameter values as the output. So kind of working backwards from an equation. To do this, I had to build my neural network. And the thing with neural networks is it's kind of a guessing game. There is no definitive right or incorrect way of doing it. So for me, I found that having 64 dense layers as my input had worked the best and gave me the best results. And essentially what a dense layer is each dense layer has neurons in it, which compute some matrix vector analysis. So each output from the first layer is the input of the next. And it's trying to get rid of its loss function. So as it goes on, the loss function should ideally be getting smaller and smaller and smaller. Additionally, I have trained it to go through 50 epochs, which is essentially how many times the neural network goes within itself and runs it. Again, kind of a guessing game as to what values and how many epochs would work the best for your neural network. I just found that mine worked best at 50, and I will credit Lydia for the neural network outline. It was amazing. So finally, what I did was I had trained my neural network to have a really good response to certain parameter values, and I then graphed the results from these predicted values. So what I did was I took training data that I used to have it learn what the inputs and the outputs should be, and then I said, okay, I have these current values. Tell me what parameter value should go into creating these current values based off of real data that I had already simulated. And then I graphed it. So this black line would be a perfect prediction. If it worked perfectly and there was no errors, this is what we should observe. And then the blue dots here are the training data, and then the orange dots here are the test data. So as you can see, the neural network did a pretty good job. In this case, it's for the oxygen-sulfur ratio. It did a pretty good job at testing this ratio, and additionally for temperature. So there are still assumptions to be made about the input of this data, and there are some conditions I made for its initial trading. Some of this would be the incidence angle being 0 degrees. I trained this saying that the ions are coming straight into the Faraday cup or straight into the first cup at an incidence angle of 0 degrees, which realistically that wouldn't be true for real data. I also summed the trident current values. So I didn't look at currents for each individual trident, I just summed them all together. I assumed that there was no noise or measurement errors within the data going into the neural network. And I randomized all the parameters. So instead of having like a set list of parameters, I just let the code randomize it in a specific range that would be ideal by Europa. But again, the parameter values were randomized. And finally, I measured one composition ratio at a time. So the next steps would be to modify this so the flow, it responds better to the flow angles for each individual cup for the 3 tridents, so that's 12 tridents total. I want to be better at modeling uncertainties and noise. Again, if it's too hot, there's too much overlap, seeing what it cannot do. Considering non-equilibrium and non-Gaussian peaks, I want to be able to use Voyager or Galileo data to actually train my neural network on real-life data, and that won't be necessarily in equilibrium or Gaussian peaks, so I want to train the neural network to read that and understand that. And finally, just understanding the limitations for using real data that's not perfect like the ones I simulated. And I would like to thank Mike Stevens, Srijan Das, Yami Rivera, Chad and Kathy for getting this REU set up, Harvard, the Smithsonian, the Center for Astrophysics, the National Science Foundation, and my fellow summer 2024 interns.
Fantastic, Ali. All right, questions? All right, let's go with Lucas.
So you mentioned that the end goal of the data is to determine some properties of the subsurface saltwater ocean. That's hard to say. You did a nice job saying that. What specific properties are you interested in determining from that?
Yeah, so some of these include, at least in the sense of Europa, so mine actually isn't going too much into the subsurface saltwater ocean. My job is kind of more canceling out the effects of the magnetic fields from the plasma around Europa. But for those who are actually trying to go and make definitive statements about the ocean, I would say they're looking at the salinity of the water and the skin depth or the depth of the ocean to see how that actually changes its magnetic fields.
Gianna.
When you were talking about your neural network, what is a loss function?
Yeah, so a loss function is essentially saying how much error is in, is essentially saying how much error is in the outputs that it's generating, and how much error there is. They want to lessen the error every single time. So it's using this matrix vector analysis in order to reduce that loss function every single time. So I was pleasantly surprised with how my neural network was able to at least identify the oxygen-sulfur ratio. It got to about a loss function about 0.001, which was really nice. So it did a pretty good job at training the oxygen-sulfur ratio.
So we got Rose.
Hello. Is there any sort of possible contamination that could happen from IO in the plasma at all?
I mean, the only contamination would be other plasma or ions interacting with the plasma that we're trying to observe. But again, that's what's kind of good about setting this voltage for the Faraday cups, is that if there is contamination that we don't want in, that's why we have that voltage to get rid of it. So we're only looking at what we want to see.
All right. We got Christoph.
Hey, you mentioned that you focused on the 64 dense layers and 50 epochs, and that's what you found was best. How did you decide that was best for your system?
So it's just about looking at the loss functions and seeing like the mean square error and just seeing how to reduce those as much. Again, a big part of it was due to Lydia Ahmed and her design on her previous neural network. So I just honestly played around with how many dense layers and epochs I wanted to use. So I think at first I started with 100 epochs and then 128 dense layers, and then that data was just like not working. The neural network didn't like that. So then I played around with it. I looked at what Lydia was doing. Hers was about 64, 50 as well, so I tried it. It worked great. Same with the temperature. It was the same exact neural network, and it also really enjoyed learning the temperature data, so that was nice.
All right, let's go with Rose.
For your neural network, why are the shapes of the layers none and then the number, not just the number?
I'm going to be completely honest. I'm not that well versed with neural networks. I was able to just simulate a graphic for what this neural network looked like, but I also was not sure about why there was nuns and 64s. So I cannot answer that right now, but I'm sure there's a good answer out there somewhere.
Actually, let's do Penny.
This is quick. It's quick. It's quick. So, do you have a sense for how sensitive your model is to the training data set? Since you don't have any noise or measurement error on it, I was just wondering if you have any sense for, like, how things might go awry once you add those things?
Yeah, I think honestly it might have a bit more of a difficult time learning it without such clean Gaussian peaks, because that would be one of the main issues with like having real data from Voyager or Galileo is it wouldn't be such nice peaks and such, you know, beautiful shapes. It would just be very overlapping, very dispersed. So I think that honestly it might take a lot more effort to train the neural network. It might have to run it more. I might have to change the dense layers, the epochs of my neural network to learn that better. And there might be some parameters values. For one, I will say that this neural network did have a hard time learning the velocity value. So that might be something with real data it might be worse at, it might be better at. So it's just kind of give or take on what the neural network actually does.
All right. Penny?
Great presentation, thank you. My first question you actually just answered, but I have another question, which is, does that last output shape there represent the one parameter you're getting out of this? And if so, can you adapt the neural network to give you the whole parameter space?
Yeah, so that's actually a really good question. So you can actually train your neural network. You're correct, I believe, where it is this one value would be the parameter that you want it to learn. And you can train your neural network to learn a bunch of different parameter values at once. So instead of, I did mine one step at a time because I wanted to kind of build up. So I started with one parameter value and ran it individually and actually built different neural networks for each individual parameter value, kind of just based on each other. But you could actually go through and train a neural network to, or at least try to learn all the different parameter values that go into creating that current value. I personally have not done it yet. That's something that I kind of want to look into actually for my next steps. So I'm very interested in doing that.
Okay. We have time for one more question. John.
You said that you added the three tridents together. If you were to do the individual tridents, do you have any idea whether it would take 3 times as much computer time, or 9 times, or 27?
I think that it might be dependent more on, are you asking for the neural network specifically? Yeah, I think that, honestly, I don't know if the trident itself matters on how much. It depends how you go about putting those current values, those individual current values into the neural network. If you're doing them all kind of at once, that might not take, 3 individual as much time or power, but it could. It just kind of depends on how you go about doing that. So there's different methods of doing it. So I'd say maybe, maybe not.
All right, let's thank Allie. All right, so we are going to have our first coffee break of the session. So this will be 20 minutes. We'll reconvene at 10:40. So get all stocked up on caffeine and calories. We still have a ways to go. So, all right, see everybody in 20 minutes. All right, everybody. Hope we're all energized from that break. All right, we'll have 2 more talks before lunch arrives. So, we have next up Roberto Panuco. So he's from Cal State Northridge. So he'll be telling you about some kind of more large-scale kind of historical studies here over the course of 2 solar cycles. And he's going to be taking a look at the prevalence of intense geomagnetic storms during that time. So whenever you're ready, take it away.
Hello. My name's Roberto Panuco, and as Chad mentioned, I come from California State University, Northridge. And today I'll be presenting a study on intense geomagnetic storms. For this project, I was working with my mentors, Tatiana Niembro Hernández and Nishu Karna. So to give a little bit of background, I would like to start by talking about the Earth's magnetic field. This magnetic field acts as a natural barrier against the solar wind and repels away any charged solar material with low velocities with little to no effect on the Earth's atmosphere. Intense geomagnetic storms are events that goes through these natural barriers and protections and affects us in several ways. So to be a little more specific, an intense geomagnetic storm is a solar event that carries charged solar material and an intense magnetic field throughout space. This causes the Earth's magnetosphere to go under compression, causing several phenomena to occur on the surface of the Earth, including things like the aurora borealis, and in more severe cases, things like power outages or complete failures in power grids in cities. This can obviously cause severe damage to our modern infrastructure from the induced current that these IGSs form. So it's important that we understand how these IGSs are formed and what causes them. So how are IGSs able to interact with Earth? They're able to break through Earth's magnetic field and harm us due to a number of factors, but the main ones being the large velocity in which the IGS is traveling, the intense magnetic field that it carries, and the coherent magnetic field structure that each IGS has. So while there are several events that could lead to the form of an IGS, there are 2 main ones, those being stream interaction regions, or co-rotating interaction regions, and coronal mass ejections. While these 2 events are very different, they share an important property in being able to send magnetic fields throughout space. They both achieve this in separate ways. For co-rotating or stream interaction regions, it involves the difference between slow wind produced by the rest of the sun and fast wind caused by the open magnetic fields due to coronal holes. As these travel outward from the sun, they cause an interaction region throughout space, which forms a compression region, while CMEs are caused mainly by filament or prominence bursting on the sun's surface, or in more general terms, complex magnetic structures on the corona, eventually breaking and sending large amounts of solar material and an intense magnetic field. So to talk about the steps I took throughout this 10-week REU program, I would like to talk about the methodology behind my project. So my first step was on making a code that used the SIMH index that measures the fluctuations in the magnetosphere to mark intervals whenever it dropped below a value of -100 nanotesla. I did this all the way ranging back from January 1996 to May of this year. After I got those intervals, I used several spacecrafts like WIND and ACE to gather in situ data to analyze each IGS individually. From the gathered in situ data, I was able to make a catalog and database for each of the 141 events, marking down and describing key properties of each IGS. From the database, I was able to create a transit time to use remote sensing to gather extreme ultraviolet snapshot images, as well as synoptic maps using the satellites SDO and SOHO. With those images and synoptic maps, I began to analyze the number, size, and locations of coronal holes to determine the effects that they have on IGS formation. So to begin to talk about my catalog, it's important we talk about SIMH, otherwise known as the Symmetric Magnetic Field Index, which is very similar to something called the Disturbance Storm Time Index. Both of these measure the disturbance in the magnetic field around the equator of the Earth using ground-based observatories. The main difference between these two indexes being in the resolution in which they're measured. The SIMH makes measurements every minute, while DST makes a measurement every hour. Using the SIMH values, we were able to get an estimate on the duration of each IGS to further gather data from other satellites. Some of the other variables I was able to collect were the temperature and velocity of the IGS. These two variables are linked due to the fact that the faster an IGS moves, the hotter the material will be, as well as the reason I'm specifically taking note of velocity is that it's a key factor on determining the severity of an IGS, since it opposes the magnetic force that would normally repel an IGS away from Earth. While temperature mainly tells us about the properties and behaviors of the material making up the IGS and the ambient solar wind that was there before the IGS, specifically telling us about the wind's properties and possible existence of compression regions within the IGS. So another one of the key factors on determining the severity of an IGS is its magnetic field. The stronger the magnetic field of an IGS, and depending on its alignment toward, it causes the Earth's magnetosphere to experience much more magnetic reconnections. The density mainly tells us about when packages of material pass through the spacecraft. So it tells us how large each wave of package is and the density before and after the IGS sweeps through that location. To further analyze the magnetic field, we broke it down into its three components. Of these three components, I mainly focused on the BZ, since one of the most important behaviors of an IGS is its coherent shape in the BZ component, since it directly opposes the direction of the Earth's magnetosphere. If BZ were to be weak or in a direction that does not align well with the magnetosphere, it would cause much less reconnections, which would affect Earth much less. Another thing I look out while looking at these three components is large changes in any of the components to signify the existence of a magnetic obstacle. Another way we can look out for magnetic obstacles is in the beta ratio, which is a comparison between the kinetic pressure and the magnetic pressure of an IGS system. What we can tell from this ratio is if it is above or equal to a value of 1, it's considered kinetically dominating, meaning the magnetic field of the IGS is being dragged along by the velocity. While if it's less than 1, it is magnetically ruled, meaning the magnetic field is ahead of the velocity. From this, we're able to tell what the major force of the IGS is at any given time as it passes through the measuring instruments. And lastly, I gathered the alpha ratio, which is a comparison between the value of helium and hydrogen within the IGS. This composition ratio mainly tells us if there was a filament or prominence that burst or got swept into the IGS in some way, as well as where that material came from, since helium is much more abundant in the corona of the sun than anywhere else. So this measurement was also being made by the ACE spacecraft, which had long periods in which it wasn't working. So I had trouble analyzing the alpha ratio throughout my catalog. So while each of these individual variables are indeed very helpful, the ability to combine them into one multiplot allowed us to look for patterns across each plot. Several of the variables are linked to each other in some way. Mainly velocity, density, and temperature tells us about the physical properties of the material, while beta, magnetic field, and its components tells us about the magnetic properties of the IGS and its evolution over time. So I analyzed the multiplot specifically looking for distinguishing features that could tell us about the events that contributed to the IGS, whether that be a CME or a co-rotating or stream interaction region. We are mainly looking for things that could signify a compression region, a magnetic obstacle, or a fast flow existing within the IGS. To look for those specific things, I mainly am looking at the magnetic field, the velocity, the density, temperature, and the SIM-H value. So using the gathered data from the in situ measurements from the satellites, I was able to calculate important factors such as the start and end time of each IGS, as well as being able to make an estimate for the transit time it took for the IGS to arrive on Earth. This transit time allowed me to look at the sun's surface in the extreme ultraviolet to look for coronal holes and active regions. Although for some intervals there were no correlating images to the time, which prevented us from analyzing those events specifically. Those were marked down by the red markings in my database, while blue markings signify events that were specifically interesting to me, whether that be for the number of active regions or coronal holes visible on the sun's surface, or flares and CMEs being visible at that time. So using the extreme ultraviolet images, I was looking for coronal holes in active regions. Coronal holes appear as dark regions on the sun's surface. These are directly related to SIRs and CIRs due to the open magnetic field and fast solar wind that is produced by coronal holes, while active regions appear as these very bright regions that are related to CMEs and flares. I was also using synoptic maps from SDO, which are created by scanning a line over the center of the sun over a period of 27.27 days estimately. So using the synoptic maps, so far I was able to outline 2 years worth of maps to later analyze how the quantity, size, and locations of coronal holes affect IGS formation. More specifically, I'm interested on the distance that separate coronal holes and active regions. Later on, I plan to measure the distance that separate the coronal holes from active regions, both at the boundaries and the centers of these two solar structures. So as for the results I was able to produce in this 10 weeks of my REU program, I was able to see coronal holes in around 100 of my 141 IGS events. Some of these are related to the missing images that I couldn't see, or the fact that they were too blurry to tell if they were coronal holes or not. Of those 100, around 40 of them were within the 10 hours of the prediction created by the transit time model. I believe that the reason this number is so low is that our current transit time model is a very rough estimate that does not include any fluid dynamics of the intense geomagnetic storm. And as I refine that transit time model, that number is expected to increase. So I also made a couple plots revolving about the variables. For this one, it's the magnetic field and SIM-H values. I used the Richardson's and Keynes list of ICMEs to cross-reference our observations within my database. From this plot, we're able to see the average behavior of IGSs, since we hardly ever get any IGS events that reach a value below -200 nanotesla in the SIM-H. While from this plot, it seems like there is an issue with our method of averaging the magnetic field, since it seems to be causing an artificial lowering in the averages, since all of the IGSs are concentrated right here. I also made a plot involving the velocity and SIM-H values. From this, we see a general trend revolving that IGSs with a large velocity have a larger correlating SIM-H value. There's also a natural distribution along the marking of 500 kilometers per second, showing more likelihood of producing more severe IGS events. This is due to the fact that there are a very limited number of IGS that ever reach a value below negative 300 nanotesla or above a value of 700 kilometers per second. It's very rare that we see events that ever go beyond those thresholds. Lastly, I made a plot revolving the transit time and the SIM-H value. We can see that there is a general trend that IGSs with a larger SIM-H value have a shorter transit time. This is consistent with the relationship previously stated with the velocity. As well as from this, we're able to see that complex CMEs that are made up of both coronal holes and CMEs are more concentrated on the right side of the plot, signifying that the more devastating IGSs travel faster and arrive at the Earth much faster than the less severe ones. I will be continuing this research over these next 2 school semesters. My immediate goals for continuing this project is to refine my transit time model to include fluid dynamics, add to my database the specific events that contributed to each IGS, like CMEs, CIRs, and flares, as well as adding data from solar cycles 21 and 22, and then getting around to using the synoptic maps and boundaries to do a statistical analysis on the importance they play on IGS formation. So I would like to thank the NSF for doing the grants that allowed us to be here, as well as a special thanks to Chad and Kathy for organizing the REU program, as well as a thanks to the SSXG team and my fellow REU interns for making this program so wonderful.
All right, thank you, Roberto. Questions? Penny.
Great presentation.
Thank you.
I have a couple questions. My first question is why the cutoff of negative 100 nanoteslas for picking out when an IGS was? Is there a specific reason for that number?
Yeah, so that's like just the defined number for an IGS. It's always considered an intense geomagnetic storm if it ever reaches a value below negative 100 nanotesla.
Okay, thank you. My next question is if you could go back to the slide where you were scrolling through your database.
Yes, please. One more, I think. There we go. If the video would play.
Yeah. So you have the red ones where you don't have images, and the blue ones that had interesting characteristics. What were the yellow ones?
Oh, yeah. The yellow or orange looking ones were events that had some imaging data, but it had such a short range that I was able to see coronal holes at the center, but shortly after, I was not getting any imaging data to see the evolution of its rotation.
Cool. Okay, last question.
3 for 3. Let's
you
go.
had on your results plots, you had some that were marked in stars and some that were circles, and I think the key is at the top right, and I can't actually see there's a ceiling in the way. What does that mean?
Okay, so the circles are events that do not have any coronal holes visible at the center of the sun, while stars do show coronal holes at the center of the sun. And the different colors show the number of CMEs related to that IGS. 0 are the ones with no coloring. The very light blue are 1, the slightly darker blue is 2, and the one very dark purple is related to an IGS that had 5 CMEs.
Thank you.
Anything else?
You sure?
Right. Rose has a question.
Yeah, so you mentioned that your method for averaging the magnetic field could be causing an issue. Do you have any ideas on how to fix that or replace that?
Yes. Let me go back to where I showed my SIM-H value for a sec, so it's easier to explain. A lot of slides. So basically, the way I'm averaging my magnetic field is I took the intervals, so at the start and end time, I categorized that as the duration of the IGS. But in reality, the IGS occurs around here, and this long strand is the period it takes for the Earth's magnetosphere to recover from the effects of the IGS. So due to me marking the duration of the IGS being as here to here, I'm averaging the magnetic field that is measured from wind for this entire period instead of right here. So it's like artificially lowering the magnetic field since the IGS already passed through the system, and it's like measuring the solar wind that came after the IGS.
So your plan is to essentially shorten the interval that the average is being taken over?
Yeah, eventually I would like to find a way to mark it somewhere around here. I still have no clue how I will be using Python to do that yet, but that is a goal.
Sam.
So the catalog is super impressive and looks like a ton of work. Could you explain which parts of that were you able to automate and which parts were like real by hand labor?
The catalog as in like the multiplot?
The spreadsheet.
Yeah. Oh, okay. So a lot of this was like, the only thing that was really handmade specifically by me were the intervals right here where I set coronal holes at the center because I had to manually look at the extreme ultraviolet images to see when a coronal hole was visible. But besides that, my code ran through the rest of these variables, checking for properties and the values and averaging them out. So it was mainly just my code being able to run this through. Luckily, I would hate to imagine how much time it would take to do this manually.
Any other questions? Kathy.
So you were using EUV synoptic maps for your coronal hole identification. There are also synoptic maps from XRT, although they only go back to 2006. So those are in the X-rays. Would you be able to use those in cases where maybe you don't have an EUV synoptic map?
Yes. So let me go to the synoptic maps page. So like the synoptic maps are one of the things I did by hand where I have to outline each coronal hole individually. The way the IDL code works is it just gets images that I have in a folder. So I assume I will be able to use XRT synoptic maps if I just created a separate folder and grab the data from there.
Yeah, you might get better contrast in the XRT, so it might be something interesting to try. Although you don't have as long a time period because it won't go back to the 90s. There was a previous X-ray imager though, so you could maybe get some more data, older data from the X-rays as well.
I'm over here, snuck behind you. All right. Any more other questions? All right, I have one for you. So, you've already done the past two completed solar cycles, 23 and 24. Mm-hmm. Now, sun's been around for a while, so I've been told. So, and we've been looking at the sun for also quite a while. So how far back could you go and still maintain the same analysis methods that you used here?
Well, as long as I'm able to get a SIM-H value, I don't know exactly when they started creating that. I guess technically I could also use the DST index, but it would be much less accurate since it only did intervals of an hour, which could lead to very rough averages. I could go back all the way as long as I have those indexes and correlating variables from satellites.
All right. And Kathy?
I triggered something.
This is really just a follow-up to Chad's question, point of interest. I saw a really interesting talk at the Hinode meeting about the Carrington event, which happened in the late 1800s, where the speaker had ferreted out a bunch of magnetometer measurements from places like India and Eastern Europe to sort of understand how that event had affected the Earth's magnetosphere. So there's lots of ground-based records that you could use to do like a real historical adventure here, which would be pretty cool.
Thanks, Kathy. All right, that's all the time we have for questions. Thank you so much, Roberto.
This is all done.
Actually, get a little closer right there.
Like that?
That's upside down. Yeah, you can just go this way. Here, let me help. You're gonna have to help.
Wait, like this? Like that. Oh. Hello? Can you hear me? Okay. Well, you can't, but okay.
Well, that was one part of your exit exam here.
Yeah.
So. All right. So, up next, we have Evan Perez. So, he is coming from the City College of the City University of New York, everybody's favorite redundantly named accredited university. So, he will be talking about doing a deep dive into some data that's looking at a rather peculiar property of solar flares. So, take it away, Evan.
Thank you. Thank you for my talk. Okay. Hi, everybody. My name is Evan Perez. I am a computer science student at City College of New York, and I'm a junior. I'm part of the Solar Physics REU here at the CFA. And today I will be talking about my summer project titled Data Exploration in Search of Small Pulsations in Solar X-ray Flares. And my mentors for the summer were Ms. Crisel Suárez and Dr. Chris S. Moore. Anyway, so just to give a presentation overview of what we'll talk about today, I'll talk a little bit about solar flares. Where is the laser on this? Yeah, I'll talk a little bit about solar flares, what they are, what causes them, why we're interested in them. Then we'll transition over into quasi-periodic pulsations. What are they and why we should study them? And then we'll transition over into XRT imagery, and we'll talk about how we can study quasi-periodic pulsations from XRT imagery and how we did that for my project. And then finally, give a conclusion, just seeing the results of what we found over the summer. So what are solar flares? So we can view the sun across the entire electromagnetic spectrum. And we can view it in different ranges, and we'll see different things viewing the sun across the electromagnetic spectrum. And when we view the sun across the electromagnetic spectrum, we can see different wavelengths are caused by different physical processes. And one of the events that happens on the sun where we can view a lot of these processes occurring is solar flares. Solar flares are one of the most powerful events to happen in our solar system, and they can release the equivalent of 2 billion atomic bombs that were bombed on Hiroshima. And they're absolutely massive, and as I've learned over the summer, they're absolutely beautiful as well. So, what are solar flares? So, whenever the sun has a magnetic field, just like the Earth does, sort of, except it's a little bit more complicated, a little more violent. But solar flares are caused by the reconnection of magnetic fields, and this reconnection it turns magnetic energy into kinetic and thermal energy. And during this process, the flares can be described as being the brightening of emission across the electromagnetic spectrum during this reconnection process. And we can view solar flares across the electromagnetic spectrum and see different parts of the solar flare occurring, which is caused by different physical processes occurring during the magnetic reconnection process. So here, the graph gets a little bit freaky, and we could see that hard X-rays at the bottom of the solar flare are emitted at the footprints near the surface of the sun. And this just means that very intense X-rays are being emitted in this area. And here along the magnetic field lines, which are the white dashed lines,
we can see that extreme ultraviolet and soft X-rays, and occasionally hard X-rays again, are flowing, can be observed along in these loops, or they called like arcades when you see a group of them in solar flares. And you notice that the plasma on the sun flows along these magnetic field lines. And we could view them in X-rays and extreme ultraviolet. And so when we can view the solar flare across the electromagnetic spectrum, there's questions as to what causes these phenomenon that we observe when looking at the model of the solar flare, such as what causes the particle acceleration of the plasma that flows along the magnetic field lines, what causes turbulence, or the fluctuations in the magnetic fields and the plasma that kind of go together in the solar flare. What's the exact cause of the energy release that occurs whenever the magnetic field lines actually reconnect? And sort of overlying all of this across the electromagnetic spectrum, and you're going to hear me say that a lot, are something called quasi-periodic pulsations that we can actually help answer a lot of these questions. And quasi-periodic pulsations we'll go into that, but I just want to run the point through that these pulsations can be viewed across all of these, across the electromagnetic spectrum, and can help us answer some of these questions. And for my project, I'm looking at the soft X-ray wavelength to view, to potentially find quasi-periodic pulsations. And here is just a whole view of the sun from Hinode XRT imagery. And here's a little movie I made from the solar flare that I'm analyzing for the summer. This is a class C 1.4 solar flare, medium to like low energy solar flare. I think this is really beautiful. If you ever played Minecraft, it reminds me of like going to the Nether for the first time or something. So I think it's pretty awesome. So we talked about solar flares. We talked about how they emit different wavelengths of radiation across the electromagnetic spectrum. And we talked a little bit about how there's fluctuations in those emissions across the electromagnetic spectrum. And one peculiar event that has been observed in solar flares are quasi-periodic pulsations. So first, what's the difference between something that's periodic and something that's not periodic or quasi-periodic? Something that's periodic can be described as being a motion or change that happens in equal intervals of time. So something that's periodic can be like the seconds hand of a clock, where each hand has 1 second in between each one. The next movement or change is predictable by 1 second, right? But when something is quasi-periodic, it has some periodic behavior, but it's not so predictable or not so easily, you can't anticipate when the next event or motion occurs. And an analogy for something that's quasi-periodic could be like a leaky faucet. Let's say a leaky faucet can drip water at, let's say, 3 seconds apart, but then maybe the next droplet of water happens at 6 seconds, and then the one after that happens at 4 seconds, 5 seconds, 8 seconds, and so forth. There's some period going on, and there's some pattern, but it's not super clear as to what that pattern is. And so in the context of solar flares, as we mentioned before, solar flares emit radiation across the electromagnetic spectrum, and in these emissions, there's these pulsations that occur, or fluctuations that occur in the emission of whatever wavelength you're looking at. And whenever we talk about quasi-periodic pulsations in solar flares, we're just talking about the not-so-periodic fluctuations in those emissions in some sort of wavelength across the EM spectrum. And here I'm just showing an example of what quasi-periodic pulsations looks like in soft X-rays, taken from the GOES satellite system in the soft X-ray flux sensor. And this is just showing that QPPs occur here in this detrended graph, which we'll talk about later in the slide. But what I want to emphasize here is that there's actually a couple different types of QPPs that occur here. The first being these very intense but short or bursty quasi-periodic pulsations in the impulsive phase of the flare, or the more intense part of the flare. And the more drawn out but less intense quasi-periodic pulsations that occur in the decay phase of the flare, or when the flare is sort of dying. So why are these fluctuations important to us? So we don't fully understand the solar flare model, or just like I showed before, a little picture showing the solar flare. That's not fully understood, and it's something that's constantly being added upon. So whenever we study quasi-periodic pulsations, they've actually been observed in other solar flares and stellar flares, or flares that occur on other stars. So this means that they're an intrinsic part of the solar flare, and they should be included, and we should know more about them whenever we're constructing the solar flare model. Another reason why we should study QPPs is because the behavior could be related to superflares. It's been seen that on superflares and other stars, the decaying QPPs have been observed. So being able to characterize QPPs can also help us understand a little bit more of the physics that occurs in superflares. And superflares are just solar flares that are 10,000 times more powerful than regular solar flares. So I've shown earlier that we looked at GOES, X-ray flux data, but imagery data hasn't really been analyzed in search whenever analyzing QPPs. So that's what my project has been sort of oriented around. And to do that, I'm looking at the Hinode XRT image data for my analysis. And here is an image of Hinode XRT, where its purpose is to understand the eruptions in solar atmosphere and the superheating of the corona on the sun. And here are just some details. I'm working with a certain filter with an element for my imagery. That's where my imagery has is this filter. And something to note is that it captures images every 10 seconds. So just to show again what we're looking at, this is the Hinode XRT imagery. I'll be looking at this flare right here. This is a zoomed up little movie that I made with XRTPy, a little plug for Joy Velasquez. And with this solar flare, I also have the GOES light curve, or the time series of how intense the X-ray emission is over time. So on top of the GOES light curve, I also have a light curve that's actually made from the XRT imagery, just to show them on top of each other. And the reason why I'm showing the GOES flux data is because GOES X-ray data is kind of the standard for studying soft X-rays. And so if we can compare our results with the GOES data, we can perhaps verify and compare with something that's a baseline in the community. And so, as I showed before, there was that light curve that I made. And this is made from the pixel values of the imagery. So as I said, all the imagery is taken 10 seconds apart. And with each image, we can create a histogram of the value of the pixel values, what they're made up of, from the low pixel values that occur more frequently and the higher pixel values that occur less frequently. And we can get this light curve that actually shows all the phases, that shows the phases of the flare, from the pre-flare phase, where it's not so crazy, to where it gets a lot more intense in the middle of the flare and dies down towards the end. And something I want to note here is that the instrument did shut off during this period of time, so it was not collecting data. So that's what this gap in the data is. And so with that light curve, we can analyze a certain part of it to look for QPPs. And I'm looking at the part of the pre-flare phase and part of the impulsive phase of the flare. And the reason why I'm looking at this region is because the times between the images aren't continuous throughout the entire solar flare. So this region right here is, and what I mean by that is that even though the images are meant to be taken 10 seconds apart, sometimes that's not always the case. And so this is a continuous range where the time between each image is 10 seconds. So how do we find pulsations in this light curve? So we want to find the fluctuations in the emission. And one way we can do this is by emphasizing the difference between the original data and, let's say, a general trend of the data. And we can do this with something called smooth filtering, thanks to Savitsi-Golay filtering, which basically just means that we can take the original data that has a lot of noise and create a general trend or smooth curve of that original curve. And this was done with scipy.signal.scipy.filter in Python. This is all in Python, by the way. So once we have the smooth filter, and once we have the original data, we can actually subtract the two And this will give us what's called a D trend. And what this does is just emphasize the difference of the trend and the original data. And that first plot that I showed of QPPs is a D trend curve. The one that was like blue and yellowish when I was explaining what QPPs are. This is the same type of curve that we're looking at here. I'm just showing here, and here I'm just showing the yellow curve with the blue curve on top of it to show you can see there's a little bit of a difference. It's not too, you can't really tell the difference really that much, but when you subtract them, the differences are a lot more clear. And this is just a zoomed in version of that D-trend curve. And as I mentioned before, D-trend is just the original data minus the smooth data. And what we can do with the D-trend curve is we want to find the periods between the peaks. And so first we have to find the peaks in the D-trend curve. And I use the scipy.findPeaks, which finds the local maximum in a window across the entire D-trend curve to be able to find these peaks and label them and record them. And here I'm just showing that we put something that is potentially that's potentially quasi-periodic, which is hopefully from the D-trend, against something that is periodic, being a sinusoidal wave. And the sine wave was actually set with a frequency of 1/20 because 20 seconds just happens to be the most common period that occurs within this D-trend curve. And so the peaks on the sinusoidal wave match the most with as many peaks as we could get it to match with the D-trend curve. And we could do the same thing by taking the derivative of a window throughout the light curve and plotting that. And it's a similar process. But this time it just emphasizes how much the curve is changing in a certain window throughout the light curve. And here we're just showing the same thing. But what I really want to emphasize is that we want to use the D trend for our analysis. And here, as I mentioned before, we use GOES light curve data. We can actually perform a D trend on the same area of the flare, on the same time frame as the flare, and get a D trend. But the GOES data is taken at a higher rate, for like 1 second, so we had to resample the GOES data at 10 seconds so that we can match the XRT cadence. So finally, for my results, we can see that the patterns in the XRT data are a lot similar to the ones in GOES. With the auto peaks, with the peaks that were automatically found, they're very similar to the red, which is the GOES XRS X-ray sensor data. The blue is just showing that I manually labeled the peaks at first before doing it automatically as a verification. And we can see that there's a period between 20 and 50 seconds that have a considerable amount of data points. So future work, I'd like to compare. There's a lot of work to do in the future. We can compare the derivative data as I shown before. That's not fully done yet. We can adjust our smooth filtering parameters, and we can perform detrending on the original data, but with a threshold applied, which just means we're looking at a certain value of pixels above a certain number, like 600. And finally, we can analyze the decay phase of the flare, as QPPs can happen in either phase of the flare, in both of them, or one or the other. So I just want to thank my mentors, Chriselle and Chris. They've been amazing and so patient with me this summer. Brendan, who's also been in our research group, he's been really, really great doing his presentations and giving me some pointers. Joy Velasquez for XRTPy, very, very helpful in making all my plots and movies. Dr. Chad Matson and Dr. Kathy Reeves, they made the solar REU just a really great experience overall. And I want to thank the NSF REU at Solar Physics Program at SAO for funding my internship this summer. So thank you very much.
All right, fantastic work, Evan. Questions? Kathy, right off the bat.
So it seems to me one of the advantages you have with using the imaging data to look for QPPs is that you can examine different parts of the image and see kind of where the QPPs are coming from. It sounds like that's maybe your next step with the thresholding. Do you have any feeling, I'm sure you've watched that movie like 1,000 times, do you have any guesses or hypotheses about which areas in that flare might be the most interesting for looking for QPPs?
So it's a very interesting point. So QPPs, it's not very they're not explained. The physical mechanisms that cause them can be caused by a bunch of different things that happens in the flare. one of the things that my mentors emphasized was that QPPs can be caused by like repetitive reconnection of multiple field lines happening at the same time. It could be something that happens interaction between the plasma and the magnetic field line that it's traveling through. So I can't say for sure what it is just by looking at it, but what I can say is that being able to pair multiple observations across different wavelengths to look for QPPs is a very common thing to do, and it's something that's very helpful. And so being able to pair that with XRT image data is potentially, it could add a new tool to possibly answering that question.
All right, it's a reminder to people online that you're welcome to put questions into the chat. Also, Evan, you're getting a lot of congratulations from Chriselle and Jonathan McDowell, so
thank you.
Killed it. All right, so Jason.
So when you show the detrended curve, it appears to be there's a lot of peaks before the flare starts. Does it mean this QPP is going on without flares as well?
So they can be seen throughout all the phases of the flare, but in this specific detrend curve, possibly not, possibly yes. We don't know.
I guess along the line of the Cassie's comment, if you do the same analysis on the sort of quiet region and whether you see the similar pattern, then I guess that would tell you that's real or just everywhere kind of thing. About the analysis, when you compare with the goals, you mentioned that you sample about the same way XLT cadence, but doesn't XLT sort of integrate during the 10 second? In that case, shouldn't you not sample, just integrate during that 10-second period of goals? I guess I'm trying to understand what you mean by sampling.
Yeah, okay. So just to be clear, just to reiterate, the original XRT cadence, every image is taken 10 seconds apart. So each data point in our light curve is taken from each of those images 10 seconds apart. And so when we're looking at the GOES data is in about every second there's a data point. And what we do is resample the GOES data. We input it we input the resample for 10 seconds and then take the mean in the 10-second interval. And that gives us the resample that hopefully matches closely enough to the XRT cadence. Does that answer your question?
So you said you took the mean. Don't you have to take the sum? I guess it may be the same. I can. Yeah, that's what I was asking you. When you say XLT was taken every 10 seconds, but it was integrating during that 10 second, right? The image.
Integrated? I don't think I understand.
The exposure was each image was 10 second or what?
Oh, the exposure between each image, it fluctuates throughout the curve. So the instrument changes the exposure time throughout. Like if it gets really bright, then it'll lower the exposure.
Oh, okay.
But that wasn't really taken into account for whenever putting like the curves.
Oh, okay. Yeah, it's a little bit long. Yeah. Yeah. Okay.
Yeah, each image was like 1.4 second exposure to like point something second exposure, or there's like a longer exposure to that. It's in like a few seconds. It's not like 10 seconds exposure.
So my point was when you compare with the goals, don't you have to do sort of similar window? Just grab the data from those same exposure window and then sum them up and then compare it. Isn't that more apple to apple comparison? That was all my point. Yeah.
Sorry.
Cool.
That's fine. All right, Brandon Aquino online says, great talk, Evan.
Thank you.
Any other questions? Nick.
Yes, I agree. Very good talk. Naturally, you're analyzing the periodicity of your signal. Have you considered using any sort of Fourier analysis, or are you interested in doing that in the future with your data set?
Yeah, so in some papers it's mentioned that they do like a Fourier series analysis. But as of right now, this was just what we were looking at for detrending. I would like to in the future, but we still have to talk about that.
Mm-hmm. Okay, and the other thing I wanted to ask is, the XRT field of view is very small, and it can shift a bunch. Have you considered maybe looking at whether certain parts of the flare that are producing the QPP might be getting clipped in some frames versus others, and could that perhaps affect some of your analysis?
It could. That's a very good question, but that's something I would have to look into further.
Okay, thank you.
We have time for one more question. Sam.
Nice talk, Kevin.
Thank you.
You showed a plot where you had a time series of both GOES and XRT overlaid. This one, yeah. So there are two peaks in the GOES curve, and the XRT one isn't picking up that first peak. Is that because GOES is seeing the whole sun and there's another flare that goes off, and XRT only gets stuff from a certain region?
I'm not completely sure about that, but that's something I can look into.
Do you have a question back there, Chris? Also, shouldn't you be in Cape Town? Oh, okay. So,
I was about to say, I saw him walking, I was like, what?
I know, I did a double take too.
Huh?
Typically for constant periods. So we do wavelet analysis, which can compensate for the quasi-periodic nature of these transients. And so Chriselle has done that on a regular basis, and that's the next step for Evan.
Thanks, Chris. All right, if there are no other questions, we can actually go into lunch, which is, we got a whole stack of stuff outside waiting to be brought in. So we're going to have a 1 hour lunch. Actually, first, let's thank Evan again.
Thank you. Thank you very much.
So we're going to have a 1 hour lunch period. So we got plenty of sandwiches and all sorts of goodies. So that'll be brought in here in just a second. Students get dibs. So they get to go in line first. So wait for them to get their lunch, and then everybody else can get theirs. All right, we will reconvene at 12:30.
like delayed though? Is it delayed when it comes back on too?
Yeah, it's a little delayed, so probably get started now. All right, welcome back, everybody. Hope we are replete and full of nutritious calories. You'll need it for the next set of talks going through. All right, so right now we're going to go through our second half. So this is our afternoon session. We're going to start it off with our second of two engineering talks. So this is going to be Abby Mervine. She is from Winthrop University, all the way down in South Carolina. And she's going to be talking about the fun time she had dealing with some X-ray optics. So take it away.
Hi, so as he said, I'm Abby Mervine. I'm a math major and physics minor at Winthrop University, and my mentors were Peter Scheimitz and Ed Hertz. And my project was energy performance as part of developing a grazing incidence telescope design system. So, as just an overview, my work focused on understanding and modeling the the energy performance of grazing incidence mirrors as a step towards developing grazing incidence telescope design system to then assist in the development of these grazing incidence optics. But why? Why do we do this? So it's essential to kind of understand how an optical system is going to perform before we actually make it. This is because this allows us to test our ideas easier before actually making it, because otherwise you'd have to make the thing, test the thing, realize what's wrong with it, make it again, test it again, and that's a whole lot of work. This also then minimizes the cost of the development of these, because you're not having to make it so many times to test it just to find out something's wrong with it. And overall, this just helps the whole design process and development process run a whole lot smoother. So now you might be wondering, what is grazing incidence? And also, what do you mean by energy performance? Well, these are great questions that I would love to answer. So grazing incidence is actually the reflection of radiation at these very shallow angles called grazing angles. And these angles are actually measured from the surface rather than the normal as typical incidence angles are. We use grazing incidence to typically collect X-rays because X-rays are very high energy. So at normal incidence angles, X-rays will go straight through a surface. But at these very shallow angles, it actually increases the path length of the photons and helps that the photons will interact with the surface and actually allows for more chance of those photons to be reflected. So this is just an example of normal versus grazing incidence. So you can see here, this is just X-rays going straight through. And at grazing incidence, this is a very exaggerated angle. They're actually normally only about 0 to 5 degrees from the surface. That 5 is like the max. After that, it doesn't work anymore really. So that's actually probably kind of exaggerated. And these grazing incidence optics are often used in astronomy to study high-energy astronomical objects, such as black holes, neutron stars, galaxy clusters, and various aspects of the sun as well, hence the solar REU. So the most common type of grazing incidence optics is Wolter 1 type optics, which involves double reflection of these X-rays to focus them to a single point. They're first reflected off of a paraboloid surface and then reflected off of a hyperboloid surface. And this is kind of like a diagram showing that. And typically when we think of a paraboloid lens, you typically look at this part. Well, actually in grazing incidence optics, we're looking at the edges of it instead. So this is the edge of the paraboloid, and this is the edge of the hyperboloid. And then here's just a more simplified version of a diagram to show what this is. So these would be your paraboloid and your hyperboloid mirrors. They're just not shaped that way in this picture. And they doubly reflect into a single focus point. Now, one problem you see with this is that there's a ton of empty space here, where if any rays go in there, they're just going to not focus to that point. So one way we improve upon that is we nest these mirrors to look more like this. So as you can see now, we have all this area here where all these X-rays are being focused to that point, and there's going to be a lot less empty space in the middle. So this overall increases that collecting area of the optic. And then just to show a bit better of a diagram of this, this is Chandra. And this is typically how these mirrors look. The 2D diagram, I feel like it's difficult to understand what these actual optics look like inside of a telescope. Typically they're in these circle shapes. So you see this first circle would be your paraboloid, and the second one would be your hyperboloids. And this is the actual Chandra mirror assembly as well. You can see all those different nested mirrors. Typically, the paraboloid and the hyperboloid would also be together to look like one tube, and you would be able to see a slight line in between them where it changes the type of mirror it is, rather than here where there's an actual gap that typically isn't actually there. So now, getting to what do I mean by energy performance. Well, in this work, energy performance of grazing incidence optics was characterized by reflectivity and effective area. So reflectivity is the percentage of radiation that is reflected off a particular surface, because some of this radiation could be transmitted or refracted or such and such. So not all of it is always going to be reflected. And then effective area is just the portion of the telescope's collecting area that effectively focuses this incoming radiation. It's different from collecting area, as in collecting area is more like your geometric area in which the X-rays can come into the optic and be focused. But your effective area takes into account your reflectivity, so that it's really only counting the amount that is going to actually be reflected, not the amount that could be reflected, if that makes sense. So in my specific work, I did effective area. I calculated effective area as collecting area times reflectivity squared, and it's squared because it's doing that double reflection within the optics, so it's being reflected once as a reflectivity and then reflected again. So you have to multiply it twice. Some affecting factors of reflectivity and effective area could be the energy of the incident photon. Higher energies result in lower reflectivities. Grazing angle, as I said earlier, like if we go much above 5 degrees, you won't see much reflection of these X-rays at all. Material of the reflecting surface can also affect the reflectivity, and the surface roughness can affect the reflectivity. Ideally, we want perfectly smooth surfaces. We typically don't get them to be perfectly smooth, but that would be the ideal scenario. So next was my data collection and cleaning. So my data was collected from the Center for X-ray Optics X-ray database, specifically their tool for a single layer mirror. Some parameters I used, the layer material I used was iridium, and we chose this because it's a very commonly used layer material. It has a very high density, and this higher density allows for more interaction between the photons and the material, which often lends to higher reflectivities. The substrate material is silicon dioxide or silica. This is just a very commonly found material, and it's very easy to use in these optics. Layer thickness, I went with 5 nanometers. This is because typically the thickness of the layer is from 0 to 10 nanometers, so 5 nanometers seemed like a good average to go with for the purpose of this project. Roughness, I did go with ideal roughness. I didn't get time to really look into what would happen if you change the roughness, but I can tell you that typically we want 0.4 nanometers or less for X-ray optics. If it's much more than that, we're going to get very bad reflectivities and very low reflectivities. And then for this specific website that I was using, the database, they asked for like grazing angle or energy, and then the amounts you're doing it in. So in my case, I was scanning over grazing angle, which means it's just going to take like a continuous scan over the grazing angle and like split it into however many parts I want. And I did it from 0.1 to 2.5 degrees, because that's the typical degrees we're working with. And then the n over 20 minus 1, that is only because that's how many points I want. But in this case, it's the number of total points I want in my universe, so I went with 200. So I did 200 divided by 20 energies, which is what I worked with, minus 1, because it says steps. So it's counting that first data point as kind of like 0. So it's going to add like 1 extra one to it than what I think. So then with the energies, it took it for fixed energies. So I did it for fixed energies from 0.5 to 10 keV, which is the typical range of X-rays we look at. And I did it in intervals of 0.5, because much more than 0.5, I would have had to do like over 20 of these and then put them all together, and that was a lot. So I just went with 20. So this database gave me data that was in the format of angle, reflectivity, and transmission, which is great. But I needed angle, energy, and reflectivity. I didn't care about the transmission, and the energy wasn't included. So I worked in Python to write some code that would help me fix this. And I used that code to first change it to angle, transmission, reflectivity, so that reflectivity was in that response kind of spot. And then I replaced transmission with the appropriate energy for each data file. And then I combined those data files all into one together file with all the energies. And that looks something like this as well. And I like to point out, it kind of has like this dip shape here, I think. And then it kind of goes up and then back down again. It does make sense for the higher energies to have very low reflectivities, even being mostly 0 here, because they're just very difficult to reflect. We often can't reflect them well at all. So then I went on to use multiple linear regression to model this data. Multiple linear regression is just a method used to model the relationship between a dependent variable and multiple independent variables. It typically follows this format for an equation where the beta values are estimated parameters. These parameters are typically estimated using least squares regression, which is a method that will estimate the parameters by minimizing the residual sum of squares, which you can see here by this equation. It's just the sum of the actual values minus predicted values squared. And this just gives us a number that it can try and minimize. I did also use other criteria besides RSS to evaluate my models throughout. I used the residual standard error, the coefficient of determination, and the Akaike information criterion, and the average absolute residual to also evaluate my models. So this is the first model I tried. It's a very basic one to start with because I needed kind of like a baseline to be able to compare other ones to. So this one's just a very basic. It has two parameters. It has just angle, just a linear angle relationship and a linear energy relationship. So it has these three parameters. I did not include the numbers that were estimated for the parameters, just to save space on the slide. But typically in my code, it would give me numbers for these, and I would input that into the model to create the graph. So this yielded an RSS of about 6 and an AIC of about -116, which there's not much I can say about those numbers on their own. It's very dependent on the other models as well. There's no good number. It just kind of depends. But I can say that for both of these, lower would be better as we move forward. So. And then, I also do want to point out how my model so far, if you look here where it's gray and a little bit up there in that corner, that's where it's predicting reflectivities below 0 and above 1, which isn't right because it's a percentage. So that is one thing I tried really hard to fix in my model. If you were at my mini presentation, I mentioned how that was the next step I was going to be looking at. So then for this model, this is the residuals, or this is the residuals of the model I just showed. The average absolute residual was about 0.113, which this tells me that on average, the predicted values were about 13% off from the actual values throughout, plus or minus 13%. And you can see here, especially in the corners, it was very low. And then here in the middle, it has these very high points as well. The colors over here just represent the from low to high residuals. Green is the best, being 0 residual, which means a 0 error. So that means it predicted it very well, very perfectly. So this was the second model I tried. So I added some more parameters. I included a cubic and quadratic parameter for both angle and energy. This is because I looked at the graphs of the relationship between energy and reflectivity and angle and reflectivity alone, and I just looked at the shape of them to try and figure out what possible transformations or parameters I could include to fit that shape. And then typically, if you include like a cubic variable, you have to include all the ones below it. This is called preserving hierarchy in these models, and typically you have to do that, otherwise it can really mess up the model or you might like miss things. So in this one, the RSS did decrease. This is the number it decreased from the previous model. So it did go down by about 4, and then the AIC also went down by 175, which is quite a lot actually. So this model overall is better than the other one. You can see, however, it is still predicting below 0 and above 1 up here, which you can see that in this residual plot as well, especially over here in this corner where it increased a lot. That's where it's predicting over 1. It is predicting below 0 here, but I don't believe it's predicting very low below 0 because it's still very close to that green color. And then this is just a comparison of those residual plots from above them, so you can see the colors better and compare Model 1 with Model 6. So as you can see, we did from the first model, we did really decrease this spot here. It got a lot more of that green. This part did increase a bit as well. These purple areas kind of stayed the same or increased a bit, but overall this one did add more green to the picture, which means overall it's predicting those values a lot better. So moving on to even further make this better and to get it constrained within that 0 to 1 range, I used beta regression, which is just another type of statistical method that allows you to model dependent variables that are continuous, but also constrained from 0 to 1. It works really well for percentages. Typically, normally these beta regression, they use what's called a link function, which is what connects the linear combination of independent variables, which that's just what we saw with the previous models. It's just that equation with the betas in it and the variables in it. That's the linear combination of independent variables. It just will connect that to the predicted values of the response. Specifically, I use the logit link, which what that is it's the natural log of the odds of the probability, and that equals your linear combination. And this, using just typical mathematical methods, you can transform this into your predicted value equals the sigmoid function or the inverse logarithm log function, which is just e to the f plus 1 e to the f. So I use the same criteria to evaluate these models as well, except you can't use R squared to evaluate the beta models with the other models because you're transforming this y value here. And because you're transforming that y value, you can't compare non-transformed ones to transformed ones. It just doesn't work. So that number is usually unreliable in actually evaluating, but all the other ones can be used. So this was the model I used for this one. This was the best one I got. I did do 3 different beta regression models. This was the best one for the data. You can see this, I think the linear combination is simply just the one that I used in the previous model, but now it's being put into this function as well. So overall, from the previous model, it did decrease by about 1.5. And then here, it decreased by about 543, which is also quite a lot. So you can see this model is now predicting within that 0 to 1 range, which is great. And then here are the residuals for that model. Overall, they're a lot flatter, a lot more green. And the average absolute residual was now 0.06, which tells me it's on average predicting values that are about 6% off from the actual values, which isn't that bad. And here's another comparison of that model 6 to that model 8. As you can see, it now flattened out this whole area, and that whole area is now green because it pushed all those up to 0. And same thing over here, it pushed those down to 1 as well. So I chose model 8 as the best model and applied this to 73 data for 73 mirror shells to calculate their reflectivity and effective area. That's just a recap of effective area. And then collecting area is typically calculated in this way, where this is the radius of the initial point of the paraboloid, and this is the final point of the paraboloid. I did not calculate those myself. They were pre-calculated, but I thought it was good to include how they're typically calculated to show the difference. And then I was just going to show that typically collecting area is this area, and then effective area is just the actual amount of reflected X-rays. So this was the energy versus the effective area. The purple is your effective area, and the pink is showing the effective over the collecting area, because your collecting area is changing for each of the shells, or for each of the energy points. So it's important to show, I think the ratio shows a better descriptor of how the effective area is changing. And these were calculated by taking one energy for the set of shells and then summing them all together to get so this is like a sum of the shells, the effective area of the shells. In contrast, this one is the energy versus the radius versus effective area. And in this case, this is for each of the shells individually, so the numbers are going to be a bit different. So as you can see here, it predicts a very high effective area for high radius and low energy, which does make sense, because as you go out to higher radiuses, the angle the angle increases. And then, as you can see, there's a sharp decrease in the energy, and it reaches around near 0 effective area towards about 4 keV, which it's just really hard to collect those higher energy level ones. And I'm going to skip that for now. But then this is the ratio again of the effective area versus the energy and the radius. So this is like effective area over collecting area. And for a better view of that, this is the top-down view. So you can see it's doing very well here. The collecting area is almost, the effective area is almost the exact same as the collecting area. And down here, it's actually almost entirely different. The effective area is about 0% of the collecting area. And with radius, it's actually decreasing almost all the way down to 0 as the radius increases. And it's decreasing not as far down for energy, but still decreasing at a pretty steady state. And then just finally, some next steps. Models can always be improved. There's never really a perfect model. Then we'll work on developing a ray tracing program for this, which ray tracing is just a method used to simulate the rays as they go through an optical system. And this will be the next step in developing this design system. And eventually, this will allow a user to change various aspects of it, aspects of the mirror, to see how that affects the reflectivity and effective area. And I would just like to thank Chad and Kathy for their work in putting together this REU, my mentors Peter and Ed, the Center for Astrophysics, and our funding from NSF. And thank you.
Thank you, Abby. That was excellent. Questions? Penny came up first. Just by a hair.
Great presentation. Thank you, Abby. Do you have an idea of when the final software will be, like this research will be available for public use or for use by scientists interested in building a telescope like this?
I do not. I personally am not continuing this project. This will be continued by my work will be continued by other people. So I personally, I'm not sure of what the timeline on that would be. I think it would, I know they're actively working on projects with this right now. So I think, I would assume within the next few years, but I can't be certain of that.
Thank you.
Yeah, we're just generally big fans of X-rays, so they'll always be useful.
So if I've understood you correctly, it seems like this is kind of a model optimization problem.
Yes.
I was wondering if you had thought at all about using some sort of machine learning techniques to do that optimization, if that's anything you'd thought about at all.
I did think about that, but my only experience with machine learning is in time series, and this didn't exactly fit that kind of vibe, and that would have been like a whole new thing I would have had to go for. So that could be a very good next step in this as well for improving the model. But I think we're also looking to kind of move past the actual modeling part and get more to the programming part. So that could be something that gets looked into, but I think they're just going to more or less go into the programming part of it.
Srijan.
So I have a couple of questions. First, is there a reason why you stopped at the cubic polynomial?
When I tried to use higher polynomials, I was getting errors in my code telling me that the higher one was becoming basically unstable, and it was lending to I must say this wrong, multicollinearity, I think it was, which typically means that that's causing a lot of interactions between the different independent variables, which we didn't want in that, and it just tends to make the model more unstable. So I did stop at the cubic for that reason.
And so you showed some residues after you did the fitting. Did you ever think about trying to do an iterative fitting with the same model on it so that it's like a perturbation on the first fitting? Do you see what I mean?
I'm not sure I understand.
So let's say if you go back to a few more slides.
The last model I showed?
The next one.
This one?
No, the one after this. After this one.
Yeah.
No, I think it was after that, where you're showing the residues on the top-down view.
Oh, yes.
Yeah, this one. So you go from, let's say, improving from left to the next one on the right.
Yes.
Did you try taking that as the thing that you want to fit, and then you fit again using your polynomials?
Oh, you mean taking the data, the predicted data, and then fitting it with the model again? Is that
Taking
what
the
you're asking?
residues as the data, and then refitting it.
No, I did not think about that.
So that's like a higher order correction,
Yeah.
and that would be a slightly better model.
Yeah, that does make sense. I haven't heard of that technique before, but that does make sense, yeah. That is good to know.
Just a suggestion, yeah.
Oh.
Anyway, great, thank you.
Thank you.
We had Rose with her hand up first. These young guns with their reaction time.
It's all my white muscle fibers. Hi, Abby. Great presentation. Were you able to solve the problem of the model not fitting right at the edges, like you mentioned in the mini presentation?
Not fitting within the 0 to 1?
Yeah, I think it was more at the boundaries at the edge of the box. You said they weren't fitting right.
Yeah,
and then did you fix that
this
issue?
one, these beta regression models, they got it. I really just wanted it to fit within that 0 to 1 range, so just that vertical range.
Okay.
The rest is not. The rest I'm inputting the parameters for the energy and the angle, so it's going to be in those ranges. But I needed it to be within 0 to 1 because it's a percentage, so you don't go above 1 or below 0 in percentages. So that's what this model did solve. It's not, you can see there's no more gray like above at the top or at the bottom. That's because it's going down to 0 and stopping, and it's going up to 1 and stopping. Does that make sense?
Yeah.
I'm afraid that's all the time we have for questions, so let's thank Abby again.
Microphone. Yep. I forgot to have it on.
All right. Next up, so thanks to the miracles of modern medicine, we happen to have Rosalie Williams here. So she is coming from Cal Poly Pomona. And she's going to talk about radio bursts. So enjoy.
Hello, my name is Rosalie Williams from Cal Poly Pomona. I'm a rising senior, and I'm going to be talking to you about a long-standing mystery about the location of type 2 radio bursts on coronal shock waves. So first, let's talk about CMEs, or coronal mass ejections. Coronal mass ejection is a mass ejection of plasma from the solar surface, easily viewed in the 304 angstrom band, as you can see in the GIF here. And they can also produce a radio burst, which this event does. And they can also produce a shock. But why study a shock? Well, they can tell us some interesting things about, say, electron acceleration and other astrophysical shocks, like this one here in CAS A. But anyway, a CME shock is a supersonic bubble-like wave with an assumed homogeneous surface. As you can see here, it looks hemispherical. And just going forward, I need to explain some terminology. We have the shock nose, which is that tip of the shock that's facing radially outward. And then we have the flank, which is the sides of the shock. So type 2 radio bursts. What a mystery. We can see an example of one in the top right there. Those two bright red lanes is our characteristic shape of a type 2 radio burst. We have a density dependence for that, whereas we have the density decreasing as we go outwards from the sun. We also have the frequency decreasing as well. Type 2 radio bursts are produced by density instabilities due to electron beam acceleration. And these are very localized events. That localization is assumed to occur at the nose. And if it occurs at the nose, it tells us some very useful information. However, that's just an assumption. So for this event, the radio burst was observed by Almaty and SSRT. I'll get into that a little bit later. But I want to talk about their localization a little more. So like I said before, they're assumed to occur at the nose. However, it's the purpose of this project to test whether or not they do. So each lane emission in the type 2 radio burst shows the front and behind the shock front. The distance between those lanes gives a compression ratio chi, and that essentially tells us that it's a localized event. But why do these localized things occur in such unstable, turbulent environments, as we can see here in the 171 band for the event? And what does the localization tell us about the environment? Well, it can tell us stuff about the electron density in the environment, for example. And these are useful parameters to get out of something, out of this event. So before I get into the actual project and the work, let's go over some background aspects of our analysis. First, we have difference imaging. Difference imaging is essentially just subtracting the previous image that you have from the current one, and it lets us get a really clear view of the shock. So here we have the image in AIA, and then here we have the difference image. You can see the shock a lot better in the difference. Next, we have a little bit about wavelength bands. We are primarily looking at the helium-2 and iron-12 lines, and you can see the wavelength response function for SDO/AIA right here for iron-12. And again, like I mentioned before, we're using Almaty and SSRT as our radio telescopes. They're part of a global network called eCallisto. They're both located in Eurasia. They're ground-based, taking data in the hundreds of megahertz range. So finally, our event happens May 9th, 2014, about 2:20 a.m. And this is the alignment of our telescopes. We have AAA/SDO and Earth in our radio observatories, the south portion right there. And then on the other side, we have stereo A on the right, stereo B on the left. And we have our shock happening right there, sort of occulted by the sun in the AAA perspective, and in full view in the stereo B and stereo A perspectives. So each of these observatories is observing this event in the low corona area. In the 193/195 and the 304 bands. The 193 and 195 is the hotter portion, so that actually gives us the picture of the shock. And the 304 angstrom band gives us a picture of the prominence, which is important, and I'll get into that later. But the other really important thing about this event is that it is occulted by the sun. And that occultation from the radio observatories in AAA lets us narrow down the location of the type 2 radio burst. And it's also worth noting that our observatories have cadences, different cadences that limit our analysis a little bit. So AAA has one image per 12 seconds, and stereo A and B have an image per 5 minutes. So when I show you the movies that are made by syncing all these observatories, you'll notice that stereo A and B update every now and then, but AAA is very frequent and rapid, and it's because of the different cadences. So the goal of the project, we're going to use the solar occultation, our multiple perspectives of the event, and the radio burst timing to determine the source of the burst on the shock. So here's what the perspectives look like. We have stereo A in the middle, AAA on the left, stereo B on the right. Also, just again to reiterate, AIA on the left is also what Earth and the radio observatories are viewing at the time. And then here's the radio data. So on the top we have some cleaned up some cleaned up raw data from AMLT on the left and SSRT on the right. And on the bottom row we have those intensities plotted. And just so we can get a little bit of a clearer view of this, let's take a little slit out of this graph. So here we've got a zoomed in portion of it from delta T from 200 seconds to 400 seconds. That white dashed line is where the CME starts in AIA. It's the exact frame. You can see the start CME in the movie. And then that black dashed line is when we start to see the radio burst happen. So as you can see down here in green, that is an 80.5 second delay. So that's interesting. We'll get into that. But first we have to make a model. We have to accurately model the geometry of the shock to get a better picture. But to make a model, we have to make a rotation matrix to fit our different frames. So we're going to take a little test point from our prominence. So zooming into that prominence there, we have our cyan point from AA on the left. We use a rotation matrix as seen on the bottom left there. Rotate it to stereo V, and you can see we get a pretty good match of that little outer crab claw type shape. And then again, if we zoom in, yeah, it matches pretty well. So let's use it. So if we elaborate that into a multi-pointed model, this one specifically using 200 points, we get something like this. So our assumptions for the shock geometry is that the center of the model geometry is about 0.05 solar radii to 1 to 0.1 solar radii off the surface. It has a smooth surface shape, and it also has an ellipsoidal shape. It's also worth noting that there is an asymmetry in the z-axis, which is the up-down axis in the image plane. So we've got some questions from this. What part of the shock do we see at the time of the burst? What part is seen by AIA and the radio observatories? And are we seeing something become uncovered? So let's look at a movie here. It's just going to keep replaying so you don't miss anything. So purple on the model is the portion seen by that specific observatory. Pink is the portion that is visible in AIA. And white is the portion that is visible when the radio burst happens. So the color change when the radio burst starts, it means that we're seeing previously occulted sections of the shock become uncovered. And this essentially means that it eliminates the nose as a candidate for the shock. Just to make that a little clearer, let's take a still. So right here is when the radio burst happens. And as you can see, when it happens, when we view it in the radio observatories, the nose is already there, which means it can't happen from the nose. So some things of note for the event that could affect our conclusions a little bit. We have a kink on the northern flank of the shock bubble. The density is higher close to the surface of the sun than it is outwards. We also have an active region present to where the shock originates from, which could be affecting this a little bit. And coincidentally, there is the prominence as well for the event. When we see the prominence appear in the AAA frame, we also see the burst appearing. So, quick summary. Analysis of the type 2 radio burst timing with the shock model reveals that in 3D space, where the burst cannot come from. So observing the burst timing along with the solar occultation of the AAA shock, it indicates that the shock nodes cannot come from it unless there are a few conditions. The evolving conditions in the shock, there are evolving conditions in the shock that are met at the time of the burst, and so then we see it. There's a time delay for the radio emission at the nose, and that is simply why. Or some third secret thing that we just don't know. So I want to give my acknowledgments to Dr. Reeves and Dr. Madsen, Dr. Treva and Dr. Raymond for advising me on the project. And I also want to thank the NSF for funding the whole REU. If you want to view the slides, there's a QR code there. If you have any questions, comments, or concerns, feel free to email me or just ask me now.
Excellent, Rosalie. All right, we got plenty of time for questions, so have at it. I think I saw Sam pop up first.
This is a super cool project.
Thank you.
Mike, you mentioned you had these two bands in the radio burst where you said one was coming from in front and one was behind the shock.
Mm-hmm.
Is there any difference in the delay of the onset of those two? Is there like anything measurable, or is that like too high time resolution?
Like the distance between the lanes in the shock?
Yeah, like does the top lane start a little later than the lower lane or something?
I mean, well, actually I can use this. I can't use that. Let's look at the clearer picture. It looks like they appear at about the same time.
For the 2010 event, I think you want to go to Sorry, I think you want to go to the slide where you show your radio data.
Oh, okay. Is that what you were asking about specifically? Apologies. So just going off of this, there is a lot of noise. I would assume yes. However, I am not a complete expert. There's probably a paper out there that says that there is some timing delay between the harmonic and then the fundamental oscillation, but I'm not sure. And I also don't think I can observe any difference just by looking at the images.
Yeah, it's probably a hard measurement, but if you could measure it, it might be a measurement of the thickness of the shock if it's really two different sources.
Right.
Awesome.
Hands up over here.
Let's go with Penny.
Great presentation. Thank you, Rose.
Thank you, Penny.
My question is, this seems pretty complicated. Was there any part that was like had the highest learning curve or got you stuck or anything like that?
Okay, I'll answer the second portion. The thing that got me stuck was actually the last movie you saw. For whatever reason, this was giving me so much trouble, even though it was essentially an elaboration of the previous image. Yeah, that took me weeks. But having the highest learning curve was probably working with the rotation matrices and the stereo angles, which I leaned heavily on Nick for. That's my mic. There were some different angles, such as like heliographic longitude or solar. There's like HEE and HEEQ, and we just had to get the right angles essentially to get the rotation matrix working just a little better than it would have, and so that was a hill to climb.
Thank you.
Roberto.
So you had a slide showing the formation between the two satellites and Earth. I wanted to ask if there was like another formation that you think would be more optimal to view the shock in, from what you know.
Yeah, this is actually similar to Srijan's question from the mini presentation. And I'll give the same answer. it will be a formation that gives us the most occultation, but lets us see the radio burst and the shock still. So essentially a formation that allows us to narrow down where the radio burst happens even more. I don't know what that would be though.
All right. It's actually, I saw Rudy's hand up first, then we'll get to Kathy.
I had a question along that line, following up on that. Are the finding those with these conditions where you have the most occultation, and that is that really rare? And so is this event? I mean, this is from 10 years ago. Is it rare to find these, to have the data just right to start to do this analysis you're doing, or is it pretty common?
I assume it is, because having all the telescopes in a certain alignment so that you get a good 3D picture of the event, and also the occultation of the sun, like having it behind limb 2, I assume is not super common.
Awesome. Okay.
There's only one other paper on the event too, so it's not super well known. So given that, I would assume that they might be hard to look for too. So I don't know, maybe that's just like a confirmation bias, like, oh, no one has noticed that this event has happened, so there's not much stuff about it, and therefore it's uncommon. I don't know.
It's also on my birthday.
Oh, congrats.
Kathy.
So your analysis determined that the shock was not coming from the nose of the event. Do you have other hypotheses that you'd want to test out or think about for where the shock might be coming from? Like, what's the next thing you would want to look at in that sense?
I might have misspoken. The conclusion is that the radio burst could not come from the nose of the shock.
Oh, yeah, sorry, that's what I meant to say.
Oh, okay. But yeah, like I mentioned at the end, there are like the few caveats, like it could just be an evolution of the conditions of the shock that then allow the radio burst to happen at the nose. It could just be that there's a time delay or something else. So we'd have to test, I think, something that we're going to do in the future is measure the intensities on the outside of the shock, on where the shock front is happening, to see if there's any evolving conditions there. And we're just going to try and really tear it apart as much as we can.
Sam. Oh, yeah. Yeah, I already talked. So, let's go with Laura.
How did you make the GIF where you show the white, pink, and purple like viewpoints of the different instruments?
Oh, yeah. Let me show it again because I'm so proud of that GIF. Thank you.
It's amazing.
Yeah, so essentially it is just a set of data points that is moving according to a certain velocity that is inputted. And again, sorry, I didn't mention this, but the ellipsoidal shape is due to it having a higher velocity radially outward. But the colors are different selections on the data based on, like, is it seen in AAA? Is it seen at the time of the burst? Then it colors that section, keeps it colored, and so all the points carry the color as they keep going. A bunch of if statements, basically.
Yeah, it's a really neat video. Let's go with Sam and then Penny.
Have you, over the course of your project, come across a NASA mission called Sunrise?
Heard about it.
So their science goals are exactly to tell apart this, but like when the shock's much further out in space.
Mm-hmm.
And the hypotheses are, does it come from the nose, does it come from the flank? So if you have any opportunity to connect with that team, I'm sure they'll be very interested to hear about your work.
Okay. Thank you for letting me know.
All right. Penny?
To what order did these gifts here take any possible acceleration of these data points outward into account, outward or in a different direction?
Like if there was a acceleration to the velocity?
Right.
It does not take it into account at all. But looking at the movies without the model on top of it and trying to fit varying velocities, you can kind of tell that there is an amount of acceleration, especially at the beginning, that slows down towards the end. And this specific velocity where you have 1,200 kilometers per second at the nose, then 850 on the flanks, seem to work the best for the entire event. But yeah, there is some acceleration there that we could also fit.
Thank you.
Any other questions? All right, if not, we can go to break early. So thank you so much, Rose. You're a real trooper. Last break of the day, so we will reconvene at 1:40 p.m. All right, so have fun schmoozing, everybody. Oh, yeah. Let me deal with that. Buddy. All right, we're in the home stretch. We have our last two talks here. So, so this is Laura Garabito. She rolled in all the way from across town in Tufts. So, and she's going to talk to you about particle distributions and some. And if you really like spherical harmonics, you're in for a treat. So, all right, go for it.
So yes, Chad mentioned I'm Laura, and my mentors are Michael, Streeter, and Christoph, and I will be talking about particle distribution functions, specifically of the solar wind and novel EDF reconstruction methods. So I'm going to start with the particle distributions that are coming from the solar wind. So the particles I'm going to be looking at will be in different parts of the solar wind. So the solar wind originates obviously from the sun, and they follow the magnetic field lines that come out of the sun. There's two types. The closed lines keep the plasma, the solar wind, close to the sun, and then the open field lines is what takes the solar wind out into the rest of space. They're not exactly open. No magnetic field line can be forever open. They do end up looping around, but it's so big that we can consider them as open, and the particles follow these magnetic field lines. So the regions that I'll be studying are the corona, and then between the corona and the Earth, and then the regions near the Earth, specifically the magnetosheets. So first the corona, this is near the sun. Then the solar wind is just the area between the sun and the Earth, and then the magnetosheet is specifically this region between the bow shock, where the solar wind goes from supersonic to subsonic, and then where the particles and the pressure of the particles from Earth counteract the pressure of the particles from the sun. And all these different types of plasma have different parameters, have different ways of acting, different magnetic fields acting on them, but they can all be looked at and studied with velocity distribution functions, or VDFs, which Ali also talked about. So just to point out how important they are, and I want to talk about velocity distribution functions. So this is a typical Maxwellian VDF. If you take the area under the curve, you can get the density of the particles that you're looking at. If you take the peak value, you can get the bulk speed, which is the most common speed of the population that you're looking at. If you take the full width half max, which is this equation, you can get the thermal velocity, which is very important in knowing the distribution of your particles. I will talk more about this later. You can look at other kinetic properties. For example, you can look at multiple populations, which is what showed up in Ali's data. For example, this could be like two different populations like this. And something important is that electron VDFs and proton or ion VDFs kind of look like this. So electrons are much smaller, which, as you can see in this equation, that would make the thermal velocity much bigger. So that's that red line. So it's the distribution is wider, and they cover more phase space. And then ions are more localized because their mass is much, much bigger, making the thermal velocity smaller, which is that full width half max. So these instruments all study the plasma of the solar wind. There's Parker Solar Probe at the corona, solar orbiter. A bit further out in the magnetosheath, we have MMS and cluster. At the L1 point, we have Solar and Heliophysics Observatory and wind, and a future mission that we have is Helioswarm, which a lot of scientists here are working on. I'm going to be using Parker Solar Probe and MMS data specifically. And on some of these instruments, we have electrostatic analyzers. This is specifically the ESA that's on Parker Solar Probe. This image can look a little confusing, but I just want to focus on two things. The first is that there's a specific voltage that is on this instrument that allows particles to travel on the red dotted path and get to the detection ring. So if a particle is moving too fast, has an energy that's too high, it will keep going straight and not curve where it's supposed to, and it won't be detected. If a particle is moving too slow, it'll curve too much, and it also won't be detected. And the other thing I want to point out is that this is a 3D electron VDF data collector. So what you see in blue, it actually happens at like 360 degrees, and you can get 3D velocity distribution functions, which look like this. And the stars that are here are the different energy levels that you can get. So the instrument will change energy to collect different groups of particles. And this is what a really nicely drawn 3D VDF looks like. So what instruments have? Yes, electrostatic analyzers, all of them. So they're very important. And this is where I'm collecting the data for the project that I'm doing right now. So this is MMS, and cluster is very similar. They're both groups of 4 identical spacecraft, which is great for observational purposes, kind of like Rose's project, which use multiple instruments. This is the ESA on MMS. It's not exactly the same as the one on a Parker Solar Probe, but for the purposes of this project, the VDFs that come out of them are similar. And this is a 3D representation of the VDFs, and this is a 2D slice in the Y and Z axis of the MMS data that I was using. And then we have Parker Solar Probe. So Parker Solar Probe has the ESA that I was talking about, but it also has a Faraday cup, which is what Ali was talking about. And so that's where the PDF that I was describing earlier, that's where that kind of looks more similar to. But yeah, they both collect VDFs. They look different, but they're both extremely important in knowing the physical properties of the plasma. What happens is that the ESA on Parker Solar Probe, sometimes its data gets cut off because of the heat shield on Parker Solar Probe, and we don't get a complete VDF, which in order to get the physical parameters, we want the most complete possible VDF. And so the main goal of this project is to use basis functions to reconstruct the data that we can't see because of heat shield, or for other electrostatic analyzers, it could be any other reason that we wouldn't get data. So now I'm going to talk about that reconstruction. So it's very well known, as you had mentioned already, that spherical harmonics are a good set of basis functions to reconstruct data. So this is an example of this data set has some like lines cut off, and this is the reconstruction using spherical harmonics, and these two images like look really well. And it's also known that we can use them to reconstruct electron velocity distribution functions. So as I mentioned before, electrons have a higher thermal velocity, so they're more spread out in phase space, which means that the data that we get is more complete. So it's easier to use electrons to do reconstructions because we have a complete field of view of data complete in phase space. Spherical harmonics are also equations, a set of basis functions that are defined on a sphere. So they're defined on a complete phase space as well. So it makes logical sense to use a set of basis functions that are on a complete sphere with electrons that are distributed throughout phase space. So this is what that looks like. This is what I had done for the mini presentation, which is the reconstruction of cluster data of electron VDFs, which, as you can see, they're pretty much, for some energy levels, they fill up the entire theta phi grid. And the spherical harmonic reconstructions did work pretty well for electrons, which made sense based on how electrons are in phase space and also spherical harmonics. And so the next thing that we wanted to do was apply this reconstruction method to ions. But if we go back to the VDFs of ions and electrons, ions are more localized in phase space. They're not defined on the full like theta phi grid. Even though so it may not make the most sense to use spherical harmonics. The thing is that MMS data takes data from the magnetosheath, which has ions that are hotter than ions in the solar wind. So it's possible that spherical harmonics could work. So let's apply it. And just for reference, this is the data of ions versus the data of electrons. So as you can see, it is not equally as defined on all phase space. This is just one of the most complete energy levels of ions, and this is the reconstruction using spherical harmonics. So this is using 5 basis functions. It does not show the correct contour lines at all, so this is not a good reconstruction. And this is using 121, and so we kind of get a shape that's similar to the raw data, but there's an incorrect peak where there's not even any data at all. And why does this happen? So spherical harmonics are defined on the sphere. So if you have a really large area that's unknown and you try to apply a basis function where it's defined on that area as well, you have too many unknowns for the area that you want to, for the node that you do want to recreate, and you can get basically an infinite set of spherical harmonics to get the correct, to get your reconstructed data, which is what's happening in the previous slide. This might be the right shape, but the rest of it, we don't know if it's right or if it's wrong. So we can't use spherical harmonics. What can we do? Well, it seems like our problem is that spherical harmonics are defined on a complete space, and we need something that's only defined where the ions are. And we can do that with Slepian functions. So we can define Slepians on the exact place and with the exact angular extent that we have the ions for. Something important to know is that all Slepians are not axisymmetric. So if we have a set of data, ion VDF data that's cut in half or something, we don't want to use a Slepian function that is not axisymmetric, because then we'll have the same problem that we were having with spherical harmonics. So that's something to be careful on. And what do we have to know from the ion data in order to use the spherical harmonics? We have to know where the center is and where on the theta phi grid that center, to match the spherical harmonics onto the ion VDFs. And we also want to know what angular extent we want those Slepians for. So we can basically build these functions around our data, which is extremely useful. So that's what I've started doing with the MMS ion VDFs. And I've been doing that by fitting a 2D Gaussian onto the data and then finding the center of that. And the 2D Gaussian can help us with, we'll find both the center that we want to fit the Slepians on and the angular extent, which is exactly what we need. And to find the center, I'm going to find the average center value by multiplying each one by how many data points we have, because as you can see, the top left has almost no data, so we don't want to take that into account as much as we want to take into what are the more complete energy levels. And just for comparison, this is how much data there is in each energy shell, and there's a big difference, so we really do want to take that into account. This is the same graph, but for Parker Solar Probe data, and the white circle is that average axis of gyrotropy. And these are the Slepians moved from the pole to that axis that we want them at. And then these are the Slepians with the correct resolution to match the resolution of the data, which is how we want to apply them. So what are the next steps in this project? So I'm very happy to say that I'm going to be continuing this data, which is great because there's a lot that I want to see happen. I need to find that axis of gyrotropy. I need to get the Slepians for MMS ion VDFs. I need to do the reconstruction with the Slepians, and I need to calculate the physical properties, the moments of MMS ion VDFs in order to ensure that this reconstruction is working. And we can do that with MMS because MMS has complete field of view, and then we can test what happens if we cut off some of the data and reconstruct it, and we can see if the physical properties stay the same. And this is an example of Slepian reconstruction that my mentors did. And there's a lot of very powerful applications with this method. You can use it for any electrostatic analyzer data, including the future mission of heliosform. And the goal that my mentors are working on right now is to combine data from the Faraday cup and the electrostatic analyzer on Parker Solar Probe in order to get an even more complete VDF, and use those data to reconstruct, use both sets of data to do reconstructions and get the best possible complete VDF. So yeah, I want to thank Dr. Chad and Dr. Kathy for doing this program. I want to thank my mentors, and I want to thank all the other REU students.
Hey, thank you so much, Laura. All right, just a reminder to people online, I am looking at the chat, so if you have questions, make sure you toss them in there. All right, looks like first question is from Gianna.
What do the red and the blue areas represent on the Slebian functions? Yeah, on any of them.
These?
Yeah.
Well, they're like different like values of, like they could, I don't know how to describe this. Let me see what picture is good. But like you could assign like a value to them and then they can be, I don't know, it's like a set of basis functions, and if you add them up, they can create like any shape that you want, and if you multiply them by coefficients, each one of those colors will turn into a different value so that you can like recreate the VDF. I don't know if that was a good explanation.
John?
You're using the VDF to define the axis of symmetry. Physically, you would expect the magnetic field to define the axis of symmetry. Is there any advantage in using the field? And then a second piece is that the field actually fluctuates on a fairly short time scale. What is the sampling time that you're using for the VDFs?
I haven't looked into using the magnetic field to find the axis of symmetry. That is a really good idea. But it seems to me that the magnetic field would show up as that like axis of symmetry in the way that I'm using it. So like, but I'm not sure about that. I'd have to look into that. And the time frame is defined by the instrument. I'm not sure what exactly that would be, but I think it's like a couple of seconds between the energies. Yeah.
Kathy?
So once you have done your fits and you've gotten your physical properties out, is there a particular question you want to answer with those properties?
Well, one question that I want to answer is how, like, to what extent we can reconstruct data from. So, like, how much missing or how little does the VDF set have to be in order to reconstruct the data? As of now, it makes sense that you need to have like at least some of the center or like very close to the center of the VDF. And then the other question is combining instruments. How well can you do that?
All right, just want to give you a comment here. So Maria Paula Penagos says, great presentation. So, any other questions? Sam.
You mentioned you can have VDS with multiple populations, like multiple peaks. Does this decomposition break down for that, or could it be used to do something that's asymmetric?
I think, well, right now we're only looking at one particle, but it would be great if we could do it with multiple populations. But I'm pretty sure there's other methods of decomposing the particles already, and then from that we can do the reconstruction. I'm not entirely sure.
All right, let's go with Ali.
I think you had mentioned that you started with the MMS data. Why did you start with that data and not the PSP data?
So yeah, MMS has full coverage of its electrostatic analyzer data, and that way when we can do a manual cutting off of data and compare that to the full VDF that we already have to make sure that the method is working. PSP has data that's cut off in its field of view. Like you can see here that PSP range of data is smaller than MMS. MMS has complete field of view. And that way we can make sure that the moments we're getting are correct too.
Penny.
I'm sorry, great presentation. I'm sorry I missed the first bit of the question, so if this has already been asked, I apologize. How much of this do you think is proof of concept for other probes versus just applying to one probe or instrument here?
I think all of it is for all instruments because it's, as long as you have PDF data in this form, you can use the reconstruction method. Maybe some instruments get even more data, even more types of data, where you can use the magnetic field to find the axis of gyroscopy. That would be great. But if you have 3D VDFs or even the 1D VDF, you can use this method, hopefully. Yeah.
We have another comment from Luis Federico Suárez. So, amazing talk, Lau.
Thank you.
Any other questions? Got plenty of time for a couple more questions. Steve.
Yeah, have you done experiments where you kind of have some initial distribution and then hide some of it and then see how good your reconstruction is?
I know my mentors have done that, but that's the goal with MMS data. That's the next step. And I have done that with spherical harmonics, where like some of this data is missing. Oh, sorry. And I've been able to reconstruct that anyway. So the next step is with Slepians, but I have done it with spherical harmonics.
Any more questions? Going once? Going twice? And we're good. All right. Thank you, Laura.
Thank you.
Get another comment here. Getting a lot of love in the comments. Hold tight enough for you. So we start on time.
Come on, take your waitresses.
Yes. Yeah, there's a 2-drink limit, all right?
How's this? Yeah, it's a good spot.
All right, everybody's been so efficient with their talk so far, so we have a little bit of time here. We got about 3 minutes. We're going to wait until about 2:05 just so the people who are tuning in online can actually see the whole talk. So chat amongst yourselves for about 2 minutes.
This is terrible. I'm at my most nervous, which means I want to talk the most, but I can't talk. I'm mic'd up.
I mean, if you have a fresh sesh, for like, a stand-up or something, you just go for it. We can do an Abbott and Costello thing if you want.
I have a flight back to Jacksonville on Saturday, and I just don't know what to make of the food on the flight. How about that airline food? Thank you.
Boo!
Day job. I liked it. Yeah.
Thank you.
You're welcome.
Thank you.
You should make that your profession. Stand up.
Stand up?
Yeah.
Okay, watch this. Watch my actual profession first, please.
Oh no, we Nothing's gonna top that.
I know. That's the sad truth.
I don't even know if we should continue on just because I was so good. I don't want to spoil it.
There's a camera right next to you, so I don't know if the people watching at home know if I was looking at you or looking at the camera. So I'll look at the camera too.
To the camera, and then I'm just
You should maintain direct eye contact with the camera the whole time.
I plan to.
Yes.
Is the mic working? Oh.
It's working now.
Let me bring it up a bit closer. The author list here was copy-pasted from the AGU abstract.
I just realized you've got like 4 versions of Harvard Smithsonian. Some with the bars.
1, 2, 3, yeah. Okay, this is something that can be
All
fixed
possible
for-
variations
for-
of punctuation. There we go, promise.
Oh, Dennis, thank you. How? Okay.
All right. Let's see. Is the camera on? So it says we can only see the slides.
Oh, is it? Darn.
Oh, man. Yeah, there were some good prop gags in there you missed.
Yeah.
Let's see. We can actually get started here with an introduction. This is Penny Planet, hailing all the way from the University of Florida. So Penny is going to talk about how the solar wind relates to solar latitude. So, whenever you're ready, go for it.
Wait, okay. Thank you for the introduction, Chad. I am Penny Planet. My project is, thank you all for coming tonight. My project is, how important is solar latitude in tracking the solar wind? So let's get started with how does this thing work? There we go. What is the solar wind? You may have picked it up from some of the past few presentations. Solar wind is this stream of plasma coming off of the sun's corona, the outer atmosphere of the sun, that fills up the solar system and defines the whole heliosphere. It is the medium through which the planets travel. It's a very important structure. And I know that people here at home here at the CFA care about it and know it's important, but there at home, why should you people care? As you may have picked up from my friend Roberto's presentation, when powerful, the solar wind causes these things called geomagnetic storms, which can cause damage to our infrastructure. And as our infrastructure gets more and more developed, this becomes a bigger and bigger risk. So knowing how the solar wind behaves is important. So, what part of the solar wind am I looking on? Well, let me set the scene. Last December, Parker Solar Probe's 18th time coming into the sun. We have the sun. We have Earth. Luckily, the setup, the position of these lined up so that Parker Solar Probe was way in close to the sun, but at the same latitude, longitude as the Earth on the sun. You could draw a line from the Earth to Parker Solar Probe to the sun that traced out where the solar wind would travel. This is good. But in addition, Solar Orbiter by the European Space Agency was also at 1 AU, same distance as the Earth, but up 10 degrees in solar latitude, tracing out that same line. This is awesome. This is 3 views on the same area of the sun. This gives us a good difference in latitude to watch how the solar wind is changing. In addition to this, bonus, Parker Solar Probe, as it moved in and out of its orbit close to the sun, fell on that line that Solar Orbiter was on, which means that we now have separate tracks, 2 different streams of evolution from one latitude, another latitude, where the only difference between them is the latitude, and the longitudes line up. And the radii line up too here, because Solar Orbiter and Earth are at the same place. This is nice. So what kind of data am I using? It is all in situ. This is basically, we're measuring a plasma. We have to know how the plasma is behaving. To do that, you measure the magnetic field in the plasma. You measure the velocity. You measure its density. And you measure its temperature. And in addition, you can use the magnetic field, the velocity, and the density to construct these quantities that we expect to be conserved by the inverse square law, called magnetic flux and mass flux. And this is a good, this tells us how well this wind is actually being treated as the same as it goes from in to out. So when you see me talk about data, these are the data I'm talking about. So the ones that aren't conserved, these we have on the far left, we have its density. In the middle, we have velocity. And on the right, we have temperature. We expect them to change by these equations set out by Parker in 1958, the one that Parker Solar Probe was named after. We expect it to decrease in density, we expect it to accelerate, and we expect it to cool the solar wind. So as a general rule, this is what we expect to see in evolution. We can compare data to these results from Parker to figure out how well it's actually working with our understanding. I will also be using a model called the potential field source surface model. The input to this is we take a scan of the sun from the Earth to get an idea of how it's where the magnetic field is strong and weak coming from the surface of the sun. We can trace the lines of the magnetic field coming out, and at a certain point, we treat these lines as having all the strong ones as having crossed over, like you can see here, having crossed over, and everything outside of that we can treat as roughly radial. This lets us kind of, because the solar wind is happening outside of this whole zone, it lets us define where we expect to see the solar wind's magnetic field becoming inward or outward to the sun. And to do this, I used code from SunPy. Let's look at some data. Woo! This is, let's say we're looking down at the ecliptic, at the solar system, from the North Pole. This is, our axes here are, as you go around, well, this axis is longitude on the sun. So where are you relative to the sun, on the sun's surface? And our radial axis is how far out are you? That's in solar radii. So you can imagine Parker Solar Probe gets in real close, and the Earth is around 200, right? So this will give us the whole view of the data that I'll be using here today. Let's start with Parker Solar Probe. It's doing this weird orbit because these measurements are taken in a non-inertial reference frame. This is how it orbits in relative to the sun's rotation, right? As it gets in closer, it eventually catches up to the sun. Actually, I think it's going this way. It catches up to the sun and speeds up past it. And then when it goes back out, it's backing away from the sun and resumes what you'd expect from a elliptical orbit. The blue data here is where the magnetic field is measured as inward. And the red data is where it's measured as outward. Nice. The spirals that are drawn are these thin lines are where we expect that solar wind to be traveling as it evolves outward from Parker Solar Probe. And if we look at the measurements from Earth and Solar Orbiter, we can see that they conform to this, right? Where the blue is, where the red is, the red is. Good first step. Let's take our theta, our round axis here, and kind of stretch it on the bottom, and so we can get a better look at what's happening at different latitudes. Focus on my project, right? So again, the x-axis here it's like if you're looking at a map. You can picture a map of the Earth, of the equator of the Earth, but on the sun, because that's what we study here. And the y-axis is sine of latitude, which is effectively latitude at this close in. It just gives you a better idea of how it blows up the middle of the plot, so you get a better idea of how stuff is shaped here. This is Parker Solar Probe data. Again, same plot, same information being conveyed. It just also tells you where on the sun's surface you can map this solar wind down to. If we were to draw on the data from the other probes, we see that same thing as earlier. Remember, blue goes with blue, red goes with red. This is generally good. We can, as a base step, knowing how the magnetic field is behaving is good, but we want to know how the other properties are behaving also. So we have an additional plot that tells you how the velocity is doing. Lighter colors here are faster. Darker colors are slower. So you can kind of see, you can see fast bits and you can see slow bits, right? On top of this, we can plot that model I mentioned earlier and try to see how the solar wind is behaving compared to how we expect it behaving from the model. And we see, oh, my bad. I forgot to explain what we're seeing with this model. The blue is where we expect to see inward magnetic field from coronal holes. The red is where we expect to see outward magnetic field from coronal holes. And this white line is where it is supposed to be neutral, right? So basically, if it's passing from red to blue or blue to red in or around that white line, that means it's conforming with the model. we can zoom out to get a better view of the whole thing. So this is like the whole view of the sun. And you can see better that there is some, it does work well with where we see these coronal holes form, right? The blue bits have a blue background and the red bits have a red background. There's a couple of other things to notice here. We have faster wind towards the center of the coronal holes, generally. We have slow wind where the crossings happen. This is expected. The bit on the right is a little bit freaky. It doesn't quite conform to, right? It's not doing the blue-red thing here. That's because this happens to be an unstable region. But the part on the left is doing well, which means it's more dependable to consider different cuts of this of this whole section as similar regions of data. We're looking at the same thing. Also of note here is that you can kind of start to see some latitude differences. You can see how for the velocity here and the velocity here are not the same. And I mean, hint, hint, that might be something that we're going to take a closer look at. So I said that region on the left was pretty stable. We can look again. What I've done here is I've zoomed in on this part right here, right around from -50 to 0, and right around the 0 mark of latitude. And this is just some examples of the data I'm picking out from in the magnetic field. You see that there are all of these different cuts of this current sheet crossing, and you see that the magnetic field goes from positive to negative or negative to positive. The thing to note here is that they're behaving similarly, and that I did not use data from the crossing itself. I waited until it was past this part where it's transitioning and more where it's staying solid to actually look at the data, because it's more dependably not being messed with by that current sheet crossing or by interactions. So let's look at how these bits of data compare on those conserved quantities I mentioned earlier. So on the left we have magnetic flux. On the right we have mass flux. These are the y-axes. The x-axis is distance from the sun. And the color bar is latitude. So this yellow orangish latitude is color means lower latitude. Purplish means higher latitude. So we see that conserved quantities are conserved generally. There's here you can see that within the error bars they all match up with each other, and on the mass flux plot, you could make an argument that perhaps all the lower latitude ones are together and all the higher latitude ones are together, and there definitely are some differences between this bit and this bit, right? The extremes of these data. But generally, like, we see conservation here. That's good. Let's look at the evolution, because this is, I think, a better look at what I'm looking for, right? Is how well are things conserved and how well can we track this back to different latitudes. This is the same conservation plot as earlier, but I've plotted the data points, same color bar as before. And as a reminder, we have the inner bits are from Parker, the outer bits are from solar orbiter if they're at higher latitudes, and from the Earth if they're at lower latitudes. The important thing to note here is that there are two noticeably different streams being viewed at the same longitude, same current sheet crossing, difference being latitude, by, in this data, such that you can barely fit the model to either one of them, or I couldn't, and trying to fit a model to working out both doesn't really make any sense. It's separate things that we're reviewing here. So that works nicely into the conclusion, which is that it does matter. How important is solar latitude in tracking the solar wind? It is pretty important. You have to keep this into account. You you should never forget the latitude difference. Another thing to note here is that if you remember this unstable bit from earlier, this bit that has, on the right side, that has, predicts blue but should be red, is that time matters as well. So really it's not a three-dimensional structure, it's a four-dimensional structure. So this is important leading forward as we send more probes out there, and especially as we have that probe solar orbiter. Its extended mission, its mission is going to tilt the inclination of its orbit up more and more, up to 30 degrees, I believe, out of the plane of the ecliptic. So this is just an early look at how well can we compare in situ data from solar orbiter to data from the ecliptic. Even at 10 degrees, we're seeing a difference. What does this mean for 30 degrees? We're going to see a lot of a difference, right? We have some follow-ups. There's a lot of space for this to grow. Encounter 18, I just looked at that one slice of data that I put up on the screen. There are plenty of other places to look for data. One standout is that Parker Solar Probe did swing in and out of the sun. It had a short section of time on the in and on the out where it was taking basically radial scan of the solar wind as it traveled. That's really useful for constraining evolution because you get, one extended view of what you can dependably say is the same solar wind. There are more lineups that can happen. I've thrown a little plot that I made up here of past and future lineups that this sort of thing can be applied to, where the x-axis again is the longitude, y-axis is latitude. There's a long one this November where Earth and solar orbiter are close together for quite a while, and at the same time we have Parker Solar Probe in a similar area for at least early on in this section. So that's interesting. There are more probes than just these three. Stereo and that Rose mentioned earlier and Bepi Colombo all are taking similar data to this that can be applied to the same thing. And my data selection was, it was, there are improvements that could be made. You could pick out better slices of data. You could be careful about what bits from each probe you're picking out, making sure that they line up. I have some acknowledgments to make. So thank you to the NSF for paying me. Thank you to Kathy and Chad for hosting the REU program. Thank you to my mentors, Sam and Mike, for mentoring. And thank you to all of the other interns whose presentations you just saw for the support during work and outside of work. They made this program special. Do I have any questions?
Thanks for that, Penny. Love the wide rows.
There was a lot of space to fill.
Yeah, it's a good creative choice. Questions? Rose.
Why'd she squish me?
To be honest, you were the one I thought would care the least.
More questions.
Questions about the research, the data.
Kathy.
Do you have any guesses for what differences you might see once solar orbiter gets higher out of the ecliptic? Any predictions?
This is not something I've given a lot of thought to. So for one thing, we're at solar maximum. I don't think that you're going to see differences because of latitude. I think what you're going to see is just different structures overall. At solar minimum, I think that's where we're going to see some really interesting stuff start to occur because for those at home who don't know, solar minimum is where the sun is acting as a dipole and the magnetic field kind of works like a big bar magnet. Solar maximum, which is where we're approaching now, is where the sun's magnetic field is really complicated. And what this means is that at solar minimum, the sun and the solar wind are going to have a lot more direct trends in latitude where you can trace out different patterns. I think the cool thing about Solar Orbiter is that it gives us it has imaging tools as well, and it'll give us a better view of like the sun as image from different latitude, which is a new thing. Thank you for the question.
We got a lot of comments coming in.
Okay.
So Arthea Valderrama says, Penny Planet, you have an astronomical talent. And then there's an emoji of what appears to be an octopus. Great job, Solar. You all killed it. I am so happy. Basil Hiles Lineata says, beep, (3). I'm imagining this may have significance to you.
Thank you, Basil.
All right, and great presentation, Penny. Nice job from Colin Marasco. And then M just says, Penny, wow, you did so good.
Okay. Thank you, Corinne, and who I believe to be Mayor.
All right. Steve has a question.
I might have missed it, but there's these kind of turquoisey things in the plot in the upper left.
Yeah. Here.
Is that where the coronal holes are?
Right. That's where the model is predicting the coronal holes are.
Okay. Well, you know where the coronal holes actually are, so.
Right. That's a good extension, I guess, is like actually tracing the coronal holes. The point of it is that the model spits this out, so it's easier to just say. The model says here's what the line is, but also the coronal holes, as predicted by the same metrics as this line, are here. Also, this gives us a view of the backside of the sun. That is, I mean, you can get that out of other models, but it was simpler to go straight from the one. Thank you for the question.
Allie has a question.
Okay, this might be a kind of vague and like open-ended question. I don't remember the exact name of the probes you were describing that you used to get this data. What went into the decision-making of which probes you used?
Okay, so thank you for the question. For me, I think it was a lot of my mentors said, here's data that we can use. And I think a big part of that is that I'm at the Center for Astrophysics, which has, its hands in Parker Solar Probe and wind and whatnot. And then Solar Orbiter, I think, is the one that you're going to use if you want to see latitude differences. For me, it was like, here's data from us and from our friends.
Thank you.
Any other questions? If not, we'll end early. Going once, going twice. That is the symposium.
Thanks, everybody.
All right, I do want to give some kind of last remarks here. So, 10 weeks is not a lot of time, but that's all the time NSF gives us. So, the fact that all of these students were capable of producing such high-level research in 10 weeks is not only impressive, it is extraordinary. And I want you all to know that. What you did is above and beyond what anybody is supposed to be capable of doing. And you did it. So feel very proud of yourselves. I also want to say that every single one of you has been an absolute wonderful delight to work with. All of you are great people. Not only do I have no doubts that any of you could become an amazing researcher or go into an amazing career in any other field. You're all fantastic people. So it's been amazing working with you. I'm going to miss every single one of you. You've been an amazing, amazing REU class. And I just got to say, I want everybody to give them another round of applause.
Thank you, Chad.
Yeah, I tried. So, all right. So for the students, So we're going to give you probably like 15 minutes. And so at 2:45, if you can go into the courtyard of Perkin, we will have a group photo. So, all right.
Mentors too, if you want to be in the photo.
Yes. All right. That concludes our afternoon.